Oh, I always give it a couple seconds. It takes a few seconds to come through live, but hope everyone is doing well this not so sunny, kind of dark and cold day here in the UK. And that's it, we're live. All right, guys, welcome to workshop number 2 of our ATN Summit workshops that we're doing in the build up to our conference in March. And today we've got a pretty special one. We're going to be talking about all things Cyclops with the Foster's crew. But before I bring the guys onto stage, firstly, thanks everyone for coming. Always like to see already people going into the comments. Love that. You already know the drill. I always like to know where you guys are tuning in from. So wherever you are, put into the comments below the video where you're tuning in from. We always like to hear where people are. That's the whole point of being an online platform, is we can reach people all around the world. So put in where you're tuning in from, what city, what country. I always love to see that before we get started. Otherwise, I'll just do a little bit of an introduction to why we're doing this workshops. So, oh, we got a few people. Buenos Aires, Argentina, Mexico, Poland, Bahrain, India, Brazil. We really got a bit of a South American theme so far. Dubai. What's up, Dubai? France, Brazil, Utah, Saudi Arabia, Egypt. I love it. Keep them coming. Few Saudi Arabias, LA, Germany. Awesome, guys. Thank you guys for tuning in. Just before we get started, a little bit of housekeeping and promo, I guess, for why we're doing this. So, as you might know, we have, let me share my screen. We have this year, I keep saying next year because I've been promoting it last year, but this is a workshop in the build up to our ATN Summit, which is a 2-day conference in March, on the 18th and 19th of March here in London, where you can come and meet all of these people and all of the firms that you can hear in these workshops. It's a 2-day conference of really high-paced talks. So the idea is it's kind of like TED-style talks to talk about everything from architecture, technology, and entrepreneurship. And we're going to be covering all sorts of topics from architecture design, technology, business, influence, and even construction. We've got some amazing speakers, as you can see, from the ARD team as well. We'll be there. And some of these workshops are part of the build up to this. So you can go on the website and check out all the amazing speakers that we'll be having at the event. It's really looking like an incredible lineup. You'll also see that this is workshop number 2 in the build up to it. So we're doing these workshops online, totally free for you guys to access with some really incredible firms. So we did one with Big and D5. We're now doing one with Foster's in a few seconds. We'll have Xfigure and Speckle next. Zaha, we got Conic and Giraffe, KPF and Finch, and we've got a hackathon at the end of it. So stay tuned for all of these. They're totally free for you guys to access. You can access them here on YouTube, or you can just simply go on the ATN website and access the recordings as well. If you do want to come to the event, we are selling tickets now, and you have 1 day and 17 hours left to get your early bird tickets before the prices go up. Tickets get you access to everything. We've got student tickets as well as regular tickets. And, you know, I think conferences have been a big part of my career. Meeting really interesting people. Networking is one of the most important things you can do. And you can come here and you'll meet some of the guys that you'll meet today. So I think that's pretty much the roundup of why we're doing this. Let's get on to the actual workshop. And I think this is the perfect time to bring on to stage our tutors for today, who are from the one and only Foster & Partners ARD team. If you haven't heard of the ARD team, you can check out the episode we did with them where we actually toured the office. But they're essentially the applied research and design team where they kind of build in-house software, in-house tools. One of the most pioneering, if not the most pioneering, in-house group in the industry. And today we have Oscar, who I'm going to bring onto stage, and Wojciech from the ARD team. Guys, thank you so much for joining. How are you guys doing?
Hello.
Hi. Thank you for that majestic intro.
Yeah, that was great. Thank you, Ali.
Obviously, the audience probably have seen you guys before because we did the little the Architect Talk Live where we demoed a little bit Cyclops. But today we're going to go into a little more depth, right? And you guys are going to walk through how to get started and how to get up and running with it. But
yes, exactly. Well,
maybe for the audience that don't know, do you guys want to just explain like your roles and kind of how you guys work within the team and the office? Or I know parts of it in your presentation, but maybe just give a little introduction to yourselves.
Yeah, part of it is in the intro that we'll go through. So my name is Oscar Borgström. I've been in the team for 6 years, and yeah, do a lot of development, but also a lot of project work. Obviously our main purpose is to deliver architecture as a firm. So that's, yeah, it's a mix. It's always a mix. There's something new every week, which is
cool.
Part of the excitement of being in the group and in the company.
And Wojciech?
So I'm Wojciech Karnówka. I'm originally from Poland, and I've been with Foster & Partners and ARD for just over 2 years. I kind of split my time as well between development and projects, doing more and more work on this environmental analysis side and also geometry. But as Oscar said, every week is a new challenge. So yeah, that's us.
Yeah,
Excited to be here.
yeah, I can imagine. It's like I remember every week you come into the office, there's a new project, there's a new deadline or something new to tackle, which always keeps things interesting and lively.
Yeah.
So final bit of housekeeping from me, guys. So for those of you in the audience, let me just flick through. I love to see where everyone's from. We got Vietnam, Ecuador, South Africa, Spain, Uzbekistan, Italy, Guatemala. Always love to see Guatemala. Just was there. Rome. Yeah, we're reaching some incredible places. Guys, in the chat, as we go along, you can add your questions to the guys. I will moderate them. So if there's something that's really pressing that I see whilst these guys are explaining it, I'll jump into it. Otherwise, we'll do questions in the breaks. We do tend to break this down, so we will have little 10 minutes breaks where we'll just kind of mute and put up a sign, and then we'll come back online. All of this will be available to you afterwards as well to go through the recording. So if you miss something, you can also go back live whilst we're doing it, right? And then come back to being live. So you can pause us whilst we're talking if you want to go back. So just put in questions in the comments and I will go and moderate it. And finally, if you like this, just hit that like and subscribe button, share it with your friends. So the more people we can get this out to, the more knowledge goes around. And I think that's pretty much it from me, guys. I think this is probably the moment I'll hand it over to you. I'm definitely looking forward to this one. Remember to put your questions in the comments. And Oscar, Wojciech, I'll hand it over to you.
Cool. Let's go.
Thank you, Oli. So yeah, welcome to this workshop. We've named it Design Foster & Partners Cyclops. As you all know now, my name is Oscar Borgström, and I'll do it together with Wojciech, and we'll jump a bit back and forth, and yeah, try and teach you how to use the tool most efficiently. And as Oli said, we're from the Applied Research and Development team within Foster & Partners. So the agenda, so we'll go through a little bit of a presentation here of us, of the company, of the tool. We'll go through some case studies and why the tool is relevant and why we think it's relevant to have been released and good to use. Then we'll go through some exercises. It might go fast. It might get complicated. But as Oli said, you can always go back and look again at what we've been doing. We try to basically build scripts from blank scripts. And we try to use only Grasshopper and Cyclops, basically, just so that it's accessible to most people. And we try and explain then what we're doing as we're building the scripts. Okay. So as you know by now, we're from Borgström Partners. Borgström Partners is a global practice. We've completed projects all across the globe, and we currently operate about 18 studios around the globe, with the main base being in London. We work on pretty much all scales, from infrastructure and urban scale master plans, down to the smallest scale furniture, lighting fixtures, and even door handles. This houses 6 integrated design studios, and that kind of closely works together with engineering, BIM, design systems, urban design, and other specialist disciplines, basically to deliver innovative projects. I think there's 12 technical design teams or kind of support teams in total that provide this in-house consultancy to the design studios that inevitably design the projects. So our team is one of those. We're applied research and development, as I've said. We are a group of architects, we're engineers, data scientists, a few software developers. Historically, we've been about 1% of the company, and now I think we're 35 people. So we are growing, or have been growing a lot recently. Our expertise span a few different areas. We try to kind of group them into these 6 categories. So there's complex geometry and fabrication, which is kind of the bread and butter of what we do. And then there's more kind of experience in interaction and VR stuff. And then there's IoT and smart buildings, post-occupancy, digital twins, stuff like that. There's artificial intelligence and machine learning, obviously. There's collaboration between tools, but also how you make different groups collaborate better. And then there's kind of the performance-driven design and optimization area. And that's the area in which Cyclops obviously sits within. So there will be a lot of focus on, measuring performance in relation to design. Within this area, we have a few different tools. So traditional workflows usually involve a lot of stakeholders, and that can create quite delayed feedback loops when you're designing. And that is part of the reason why we develop these different tools, to basically shorten that time span, but also give more power to the designer so that they can kind of develop this intuition of how their designs perform, and how they can make informed decisions quickly and effectively. And while black box machine learning or AI models are all the rage these days, in some contexts like this one, fast and analytical and physics-based usually wins. Or I would say basically always wins, as long as they are within the relevant performance speed. Okay, I will hand over to Wojciech, who will talk a little bit more about the background of Cyclops.
Cool. Okay, thank you, Oscar. So how fast are we speaking, and what type of analysis? Right now on the screen, you can see one of our early experimental project. It was back in 2007, and it was the Overhydra and Entertainment venue in Glasgow. What we analyzing here is the visibility of this blue area from the stand, and evaluating one of these layouts back then of around 10,000 seats would have taken a designer a full working day. Now, 18 years ago, when we started developing this, we were evaluating 24 views per minute. Today, with the massive advances in hardware that we're building on, but also the software that we develop, we're running beyond 4 million views per minute. So we're going back to the same designer from 18 years ago. Depends how you want to look at this, but if you want to spend the whole day working on this task, you could have evaluated a bit over 160,000 variations of the same stadium layout, or you could have spent just 150 milliseconds to evaluate one option, and you could have just moved to other tasks. So here's Cyclops, our GPU accelerated ray tracing engine. Compared to other off-shelf tools, we're getting performance gains by orders of magnitude. The amount of time you would have spent evaluating a single facade panel, you can now spend evaluating entire city block. The Cyclops as a tool supports multiple analysis like view analysis, artificial light simulations, daylight simulations, connectivity, and multiple other analysis. It has a custom renderer and has integrated and automated pipeline for generating PDF reports for each of the analysis. It allows us at the office to easily compare between design options and communicate the differences between design options to the stakeholders. And Cyclops last year has been used on hundreds of projects, saving thousands of working hours and hundreds of thousands of compute hours. And this speed unlocks a rapid feedback loop, which just makes the design process faster and more informed. This is the slide that Oscar presented last. Now, we will dive into a couple of case studies just to show how we used Cyclops in the office. We will start at the scale of the facade. Now, as you know, most of the work in our industry is confidential. So instead of showing you the actual project, we're bringing a kind of a dummy tower or generic tower to illustrate the process without showing too many details. Now we were asked to help and manage the direct irradiance on the facade. So we designed a system of horizontal and vertical shading louvers. Now, traditionally, shading optimization relies on evolutionary algorithms or other heuristic methods. This is to reduce the computation time by just efficiently sampling the solution space. Now, with Cyclops, thanks to the speed and scalability that we already started talking about, we can just run a brute force evaluation of entire solution space. So we test every combination of horizontal and vertical louvers per facade orientation for east, west, north, and south, and that's done on a laptop in 10 minutes. So here you can see some of these iterations. Now, this approach allows us to plot a three-dimensional surface and understand the exact relative impact of each of the louver iterations. For example, on the image that you're seeing right now on the screen, it's very clear that the deep horizontal louvers have much more higher relative impact than the equivalent depth on the vertical louvers. And the next couple of images just show the very same exercise on different orientations. Now, another not so specific building in Asia where we extensively use Cyclops for form finding at early design stage. We began by extruding the sides to the maximum buildable envelope, and that was 120 meters, and then we ran a sunlight obstruction analysis to assess the impact of this envelope on the adjacent school. The voxels with the greatest negative impact are then removed, and then we evaluate the impact of the resulting massing on nearby residential buildings. We again redistribute the voxels to minimize the view obstruction while maximizing our own views. So the voxelized shape can then be further rationalized for public space, for connectivity and internal daylight. And this becomes a sort of a reference for the envelope that the designer can then work with. Here you can see this envelope. Now going into the specifics, you are seeing on the screen right now the distinct stages, right? So for example, on the top left, the maximum buildable envelope, voxels, shading heat map and the visibility map. On the bottom, the current side and the maximum shading envelope, and finally the combined massing. So this is quite helpful for the stakeholders, but also for the designers to understand the implications of their decisions. And finally, an example at the urban scale. This is a study for Guangming Hub in China, where the goal was to develop a layout that optimized for connectivity between the neighborhoods, views towards the central hill, daylight potential, and the total floor area. So we could have spent months creating and analyzing thousands of these options to find the best performing ones. But instead, we feed the requirements and the design rules to the computer and allow it to do the heavy lifting for us. The genetic algorithm generates and evaluates thousands of options and evolves the better performing ones. So as I said, it could have taken 3 months if done manually, but together with our distributed computing tool, Hydra, we could just do that overnight. And right now the images are actually screenshots from Rhino of the distinct analysis, so cumulative radiation view and sunlight hours. And now I will pass back to Oscar to talk specifically about the released part of Cyclops and also some of the features that we'll be testing today.
So we reached a point about a year ago where we basically believe that the industry benefits from the performance that we're seeing in Cyclops outweighs the value of our competitive advantage. So following Foster & Partners' commitment to sustainability, the plugin was released, or the environmental engineering part of the plugin was released as a free plugin to install. And this is basically to encourage widespread adoption and to basically increase the integration of more sustainable design practices across our industry. The released package includes a few different features for things like radiation and daylight, sunlight hours, as well as some quite bespoke ones like the sunlight obstruction that Wojciech has been talking about. Cyclops is a Grasshopper plugin, and therefore it fits into most Grasshopper-based workflows. And it really brings this power of the GPU directly into the Grasshopper canvas. So the benefits of using Cyclops is, obviously, as we described already, the speed at which it can run, but also the scale it can run. Not only the scale of the analyses, as in more samples, but also the scale of the context models that the software can handle. And then obviously this integration into Grasshopper, which allows for highly bespoke workflows that run analysis where the buildings often are designed. So we'll take this one as an example. This is a real-time model in New York, where we're modifying a massing and updating the analysis for each frame, giving direct feedback on the performance. So each time you move this little arrow, the analysis recomputes. To give some background on how this runs, the façade is sampled with an evenly distributed grid, totaling around 1,700 analysis points. Each point is then sampled 65,000 times across the dome, meaning that on every iteration we're tracing over 100 million rays, using a context model with over a million mesh faces. All of this runs at 40 milliseconds to give an update frequency of 25 frames per second, and thereby the real-time analysis, as you saw in that GIF. In these type of workflows, it's crucial to build highly efficient Grasshopper models. So in this example, the analysis only actually takes 20 milliseconds, and the rest of the time is spent referencing the geometry, subdividing the facade, creating the display colors, and feeding that back into the viewport. But it's really crucial. If you want it to be real time, you need to think about every little computation that happens inside the Grasshopper canvas. Cyclops aims to really minimize the unnecessary recompute. And part of the approach here means that Cyclops can retain context geometry between analysis. This basically makes it a perfect tool not only for real-time workflows, but also for optimization processes. So you can basically choose which geometry you want to update between analyses, rather than reloading everything every time. For this example you're seeing on the screen, we're evaluating 23 options per second when we run a single objective, meaning a single analysis, or 16 options per second when we run 3 different analyses within the same workflow. We've developed an extensive documentation that you can see at docs.cyclops.fosterpartners.com, which explains all the objects, the different analyses, the components, as well as a few tutorial files. For every analysis, there's a tutorial file which ships with the plugin that you can open just in Grasshopper. We obviously benchmark the analyses against the kind of standard tools that are used in the industry to make sure that what we deliver is what you expect. It can be installed through the package manager Rhino 7 or Rhino 8, just go in there, search for Cyclops and click install. You need to have a Windows machine and you need to have an NVIDIA GPU. Those are the requirements. At the moment, because we're kind of in the beginning, we ship each version with a 90-day cutoff, meaning that you basically need to update your Cyclops version within 90 days. If you're using Rhino 8, usually it just updates all the plugins automatically if you haven't unticked the automatic updates, which you can see is unticked here. But that is usually ticked, and then it will just install when you start Rhino if it finds a new version of a plugin. Yeah, you can visit cyclops.fosterandpartners.com if you want to read more about the plugin, as well as the documentation. As I said, there's a few system requirements and terms of use in there as well. And yeah, we're really excited to be able to run this workshop with you. We're really excited to have been able to release this plugin publicly, and we'll hope you try it out, or maybe you're actually running it live now as we run this workshop. Okay, I'll hand over to Wojciech, which will show some introductions in Rhino and Grasshopper, and then jump into some actual files. Thank you.
Cool. Thank you, Oscar. Okay. Cool. Can you see the screen, Oscar? So, okay.
Yeah.
Perfect. Okay. So, as Oscar mentioned before, we will start from the basics, and then the difficulty or the level of complexity will grow as we go. For this workshop, we will be using Rhino 8 and Grasshopper. I already have the Cyclops installed, but as Oscar mentioned, the Cyclops can just be installed directly from the package manager. If you search for Cyclops, you'll find it just there. You would then have to obviously restart your Rhino in order to see the Cyclops loaded. Okay, so as Cyclops is installed correctly, you should all see here in the menu ribbon a Cyclops menu. So from this menu, there's a couple of really important and really useful information. So I will maybe go one by one just to explain the easiest way to start. So the first one is this about pop-up. If I just bring it to the screen, we will see here the information on the system, and we will also see the version with the beta expiry time. So I believe in Rhino 8 as a default, Rhino will update your packages, so you don't really have to worry about. But if you have that auto update box unchecked, you will see when your beta expires. Also 2 weeks ahead of that point, you will get a pop-up, so you can just install a new version and you can keep going. We also have here an information on the GPU recognized by Cyclops and on the current driver. The next one on the list is this check for updates. So this will just bring a package manager and check if the new version is available. But most importantly, we have this documentation item. So I will just open that window to show to everyone, and I'll bring my browser back in. So now what we see in the browser is documentation. We start at the getting started page where we see the installation instruction. We see the changelog that displays the latest changes. But interestingly, we also have this Rhino 3D section where if you go to components, you can see the mirror of your actual Grasshopper components. And if you click on any of this, you can find detailed information on all the components, on the required inputs and outputs. But you can also click Learn More and find more information about any of the components. And maybe Add Object is not the most exciting one, but if I go, for example, to Sunlight Obstruction Analysis, and I go here to Learn More, we'll see quite a lot of diagrams and text explaining the principles analysis, some of the conventions that we used in the application. Also, if I use any of the components, so maybe just to demonstrate, I use one of the components, let's say location. I can now right-click on the component on the capsule and go to documentation, and what that will bring is again a part of our documentation that's specifically related to the location, right? So to the location component. So you can see the inputs and outputs. We will talk in a second about the methods that allow us to create the component in different ways, and maybe I can actually show that right away. So some of you might have been surprised, because usually when we pick a component in Grasshopper, we would just expect to see the component right away. Now, some of the components have multiple ways in which they can be created. For example, like this location component. So the first time you drop it on the canvas, you actually don't see any inputs or outputs. You would need to right click and then pick one of the methods in which that particular component can be created. And we will see in action how this is relevant with some of the analysis in a second. But this is just to explain if any of you get confused. So that's our documentation. The next important aspect is the tutorial files item. So together with Cyclops, we ship a number of tutorial files that show how to use all the available analysis. So we have examples like cumulative radiation, data autonomy. We also explain some of the conventions, such as custom data or multiple scenes. Now we'll go through a lot of these principles throughout the workshop. But if you're interested, you can just have a look yourself and see the setup, the minimal kind of viable setup that you need to have in order to run any of this analysis. But as it was mentioned at the beginning, today we will build the workflows from scratch. That also includes a little Rhino model that we will build, just to make sure that everyone is on the same page and that we can kind of start from the basics. Is there anything, Oscar, that you think is worth adding before we start building?
No, I mean, let's go.
Let's go. Yeah. Okay. Cool. Okay, so first things first, we are in meters. We have a Rhino 8 open, and just a kind of a default meters template. So what I first like to do is just to purge my model so that I remove any of the layers that are empty, and I'm just left with my default layer. So let's start building some geometry. We will build a kind of a city quarter-like simple model, just using some basic Rhino functions. So I will start by creating a parent layer called envelope, and this would be my design options, if you like. So I will start with that envelope layer, and then I'll build some chat layers. So I will call it an option 0, option 1, option 2, and maybe let's start with that. I will also maybe change their colors just to make it slightly easier to distinguish as we draw. So just some random colors. It doesn't really matter. Okay, and we will just start with a simple box. If you're following along, I will just draw something like 40 by 40 meters. That's our option 1. Then maybe option that's our option 0 actually. Our option 1 might be just similar, but instead we will split it. We'll split it in half and make it just a bit larger. So it could be really anything. Feel free to build what you'd like. I'm also going to now create another option, which is just a cylinder. So just a simple extrusion. and I'm just going to remove that curve just to have a clean model. So we have 3 different options, all closed extrusions. This gives us something to start working from. And now I'm going to build another layer, and I'm just going to call it analysis context. So in this first analysis, we will be actually analyzing context, and I will explain in a second what I mean by that. But first, let's build some forms, some massings around our proposed geometry. So I would just draw some shapes. Perfect. And I will also build another layer that I would just call a static context. So what I mean by static context is just the geometry that will also impact the analysis, but it won't be really, we won't be really analyzing. It would just be there. You can think of it as, we're designing a part of the master plan. We're thinking about one of our designs, and we're really interested in the impact of our proposals on the adjacent building, but there's also some other already existing context that maybe not so important. So let's just make that a little bit darker, and maybe our analysis context can be just like that in this brown. Perfect. Okay, so this I believe are all the ingredients we need for the moment. So if I just save this file, and I will call that sunlight hours model, just to make sure we don't lose any progress. And I will also do the same here, and I will call it perfect. So now I have an empty Grasshopper file, and the first thing we need to do is we need to reference some of this context so that we can get access to it. I will also use the bifocals. It's a plugin that will, as we drop any of the components, I'll be using icons, but the bifocals will give us a description of what the component is. Do I need anything else? I think this is a good place to start in Grasshopper. So first component that I will drop on the canvas that will do something is actually the query model object. So this is the new component in Rhino 8 that allows us quite easily to reference geometry, active geometry from the Rhino document. And I will, for now, I will just reference the geometry that belongs to the envelope layer. And I'm not going to get into the details. There's quite a lot of materials online, but these new components have quite advanced filtering capabilities, so that we can extract exactly the geometry that's required. So in order to get the objects that belong to the envelope layer, we just have to right click here on the layer and change the match method to contains. And that way I will only get the objects that belong to that particular layer. Now you will have seen that I just get a simple flat list, which is not ideal because I also want to distinguish between the objects that belong to any of these particular child layers, right? I want the branch where each of the branches represents one of these options. So this is done. This is done quite easily. We can just use the group content component, which is also the new addition to Grasshopper in Rhino 8. And here under the key, we have to define the key that will now separate these objects into the branches. So I go here in the model object category under layer. We have to find a name, right? So now our initially flat list will get split into three branches, where each of the branches represents that geometry. Perfect. So you can see now that I have my values and I have my my geometry. So we will do that more today, but this is the kind of the basic explanation so that everyone is on the same page. So what I also like to do to keep the scripts clean, I will try and keep them in separate groups so that we know that this is a distinct functionality. Now I will also do the same for the rest of the geometry. So we will do one for analysis context. And I will do one for the static context. Perfect. So now I have my geometry reference, right? My static context, my active context or analysis context, and my proposed geometry. Fantastic. So let's just move it all to the side. And now let's start building on top of this. We will want to, as I said, we will run the sunlight hours analysis, but we will run the sunlight analysis not on our own proposed geometry, but actually on this adjacent buildings. This is to help us understand what is the impact of any of these massings forms on the adjacent buildings. Okay, so the first thing we need to do is, since we already have the geometry reference, we need to subdivide this building into a grid of points, analysis points, that we will be able to test, right? So there's a million of ways of doing it. I'm sure that if Oscar was running this part, he would have done that differently. But I would just take our B-reps, I will split them so that we have access to the faces. I will, if you use Grasshopper before, I'm sure that you know exactly what I'm doing. But I would take our faces, sample them somewhere in the middle, so that actually let me keep that here. And I will also just for those of you that maybe haven't done that as much, I will show the normal vectors, right? So we taking the faces of all the B-reps, we're extracting the normals, and we now, based on the direction of the normal or direction of the surface in this case, we will extract only the vertical surfaces, right? Because as I said, we will be evaluating the facades of the adjacent buildings, so that first thing we need to remove the horizontal surfaces. Right. So one of the ways of doing that is just looking at the dot product between the normal of the surface and the z vector that's always pointing up. Right. Now what dot product is doing is, in simple words, or your intuition might be that it's just checking how aligned the two vectors are. So obviously we have vectors that are pointing both up and down, so we need to get an absolute value, and we need to also check, well, if those vectors are aligned, right? So if we have a horizontal surface, we know that the vector is pointing either up or down, which means it's aligned with our z vector, so that we can now dispatch our B-reps quite easily. Okay, perfect. So now I have access to my horizontal surfaces, but actually what I want are the vertical ones, right? So if I now hide all my geometry, and for the time being, I can also hide all the geometry from Rhino. I have my vertical surfaces. This is a good start. Now we need to think about how we're going to subdivide them. We don't really care about the data structure here, so we can just flatten the surfaces, and we can now start subdividing them, right? So we're going to start with a mesh surface component, which will allow us to take those faces and turn them into a mesh, right? If I now press Control M, I should be able to see the subdivision. So the default subdivision looks like that. As a default, it just hard codes constant U and V count. We don't want that, right? We imagine this is a kind of a proxy for some sort of a facade. So we want to now subdivide the facade into a number of panels. We can think of it as almost like maybe a curtain wall. So let's get the dimensions. First, let's get the division component, and we'll do that separately for U and V. And I will also get something like a slider between 0 and 12. So I plug them just to the division to get now the subdivision of the surfaces into a mesh, but that's driven by the particular dimensions of my surfaces, right? So right now you can see this is our vertical subdivision, and here we have our horizontal subdivision. So let's do something like we can stick to maybe for now 4 meters vertically and also 4 meters horizontally, right? So you can think of it as a kind of a window module where we have 4 meters in both of the directions. Fantastic. Now, as I said, we'll be using the geometry of our adjacent buildings to run the analysis, and we will be using these panels to visualize our results and to define the position of our analysis points. That means we cannot just draw simply the panels or sample the points exactly on the geometry, as well, geometrically it would be impossible to define or differently, the analysis point would be clashing with the geometry that we're using for the analysis. So we need to offset our analysis point, and the panel will be visualizing on slightly from the facade. So this is again something that you would have done a million times using Grasshopper. I will just maybe reuse the evaluate surface component. I will use the normal, but I will unitize it. So by unitizing, they would just be, I'm sorry, yes, I will unitize them. And that means that now all my vectors are only 1 unit long, in this instance 1 meter long. And I will also multiply now that vector by some very small amount. So I can, for example, do something like 5 centimeters. Okay, so now I know that this is now a vector that moves my base surfaces from the facade by 5 centimeters, right? So I can take the original surfaces and just move them just slightly away so that you can see the original geometry. So that when we visualize our results and when we test our points, they're not directly on the surface, but they actually slightly away. And this is a very common practice in environmental analysis. So it should be fairly easy for those of you that have run environmental analysis before. Okay, perfect. So now we have 20 meshes. Each one of these 20 meshes is essentially a separate surface. We need to do some cleaning up. So first things, let's just join the mesh together. So that will give us a unified mesh, right? We have one mesh of with just over 2,000 faces. That's great. In the next step, we need to now get access to individual panels, individual faces. And if you have any of the plugins installed, this is fairly simple, but since we're using vanilla Grasshopper, we need a few components to do it. We, instead of one joint mesh, we want actually 2,308 separate or individual meshes. So the way to do this is we need to first deconstruct the mesh. Okay. Amazing. So that gives us access to vertices and faces. We will then need to deconstruct the faces, right? So each of the faces of the original mesh is deconstructed so that its corner vertices are extracted, and then we can select the vertices in sets, so that there is one set per face, right? So maybe it's gonna make more sense if I just show it. So here we are running the deconstruct faces. So for each of the faces, we get the indices. Those indices, for example, for the item index 0, 0891, describe which of the vertices of the original mesh make up the face, right? So if I now go with list item, I can, and I obviously have to graft my inputs, so that now instead of a single flattened list, I'll get a tree where each branch defines the indices of the original vertices that will make each of our individual meshes. So in this instance, we now get the tree where each branch contains the 4 points. 4 points because we're dealing here with quads, right? So the mesh is defined by four vertices. Great. Now to build the actual mesh, we will need the construct mesh, right? So we know that they are in the correct order, and we only have to now plug the vertices, the selected vertices, into construct meshes vertices input. So to illustrate what we've actually have done, if you don't yet have this intuition, instead of having originally joined mesh, right? We now have individual panels where each panel is really just a quad with 4 vertices. That's great. I can simplify here my tree. Fantastic. Now let's try and extract the analysis point for each of the panels, so that we can actually define a point in which the analysis will be run or will be sampled. So the first thing we can maybe not even simplify, but just flatten, as we really just want access to each of these meshes. We can then use a face normals component, which gives us a center for each one of the panels, and also a normal. And we will also just group it here and say facade panels. So this is now the geometry that we can very easily visualize, for example, colors on. And here we are getting the inputs required for the analysis point. There we go. So right now we need analysis point. So analysis point is here. It's a Cyclops component. So if I press Control Alt, you can see that it's here under objects, right? And I already know that the analysis point will need position and direction, and this is exactly what the face normal gives us. So I'm gonna plug the centers to position and the normals to the direction, and then I will flatten my analysis points again. So you can see that exactly how we expected. We have 2,308 analysis points and the corresponding number of facade panels. Great. Okay, so let me group some of this together. Okay, and it's a little cleaning up. Amazing. Okay, so we now need to deal with the context that we left here. Maybe I'll move this to the bottom, and let's think about how can we bring this context and prepare it for analysis. So the first useful thing that Cyclops lets us do is this get clean mesh component. So this is a component that tries to, with as little effort as possible, to create a clean mesh representation of the input geometry. So for BREPs and SAPs, it will try to get the display mesh that is already automatically generated by Rhino. And this replaces the need of generating the new mesh every time the script runs. This will also help us when we have invalid meshes or nulls, just to make sure that we have a nice and clean mesh. Okay, so I can plug this get clean mesh into my static context, and I will also do the same for the proposed geometry. Now you can see here that this is actually the place where we care about the data structure, so I'm not going to flatten it. I'm just going to keep it as it is. And now we will also need the geometry on which basis we build our analysis panels. We will also have to include it in the analysis. So I'll also get the clean mesh here, so that we can have this added. Now the Cyclops specific part, right? So in Cyclops, you can also read about this in documentation. We need to wrap the geometry into a geometry object, which is our basic primitive in the three-dimensional scene. And it wraps the data so that the rays in Cyclops can interact with it. So I will just, and you will, by using Cyclops, you will get very quickly into the habit of using that whenever we have, here we still get the grasshopper mesh, right? So this is the same mesh you could just bake out in Rhino, but we now have to turn it into a Cyclops mesh, a mesh that Cyclops will understand in the analysis. So I'm just going to plug the our mesh into the mesh input, and then we will also need a geometry group. Okay. Now the geometry group is used to bundle the geometries and to populate the scene for the ray tracing analysis or instructions. So they can be instantiated multiple times using the transforms, and it can also contain several geometries, so that any changes made to the group properties will propagate to all geometries in it. Now, the very important thing is that is this input here, the name. The name serves as the unique identifier in a Cyclops and is used for organizing, filtering, analysis results. And these names must be unique when added to the scene. And Oscar will talk slightly later about the scene and the importance of management of the geometry. But I just want to stress out here at this stage that it's just very important that we are precise and consistent, and we take care about how we name our objects. So in this instance, this is actually proposed geometry. Okay. Perfect. So this is our little component that turns our Rhino Grasshopper native geometry into Cyclops geometry, and I will copy and do exactly the same to the rest of the context. So here I will actually bring both of those together, and I will just plug the mesh. But as I said, let's be careful about the naming of our geometry groups, and I'll call this group context. Okay, fantastic. So we're getting there. We're not too far. We have now the geometry, we have our analysis point, and now we need the actual, we need to look into the actual instruction, into the actual analysis. So here under analyze, we can see the sunlight hours analysis, which is the component we'll be using today. And once I drop it on the canvas, we can see that there is still a couple of missing inputs that we will need to provide. So first thing, I just like to start by just adding the Boolean toggle so that the run is set to false. If I set it to true, I can see that we need some scene objects or a scene, right? So first thing I will do is I can maybe drag these guys over so that it's easier to see. And I'll call this proposed geometry. And I'll drag these guys and I'll say it's context so that we know what's happening when we're over here. Okay, perfect. Now, we can also see that this is our geometry, this is our analysis points. We also going to have to provide a sunrig. If you've used Honeybee or Ladybug before, you would remember we have to have a way of generating directions towards the sun. They depend on location, and they also generated for a specific period of time. So before we run the analysis, let's actually build the sunrig together. And after that, we can just run the analysis. So sunrig is under sunrig name. This is one of those components that have multiple methods. So if I right click, we can see that we have the sunrig and we have the sunrig geometry. We'll use both, but let's just start with the sunrig. I will also then add the location. We've already seen the location component, and I will just build the location from coordinates. I think as a default, we are actually using London, which is 5148 on latitude and 0 on longitude, but feel free to provide the coordinates for the location that you're working from, for example. Then we will, as I said, we also need a time series or a time pattern, which defines specific points in time throughout the year, and is used to sample the time based on then data like weather when creating sky series. We'll look into that in a second. But just to keep things simple, let's create a time pattern. Again, there's a couple of ways in which the time pattern can be created. We will just use from schedule, which just lets us define the time pattern very simply for months and days. We will run this analysis just to keep it simple for 21st of March. Okay, and we will also do it for just, let's say, 10 hours. So that we okay. Oh, actually, instead of 10, let's do it for entire day, right? So we have 24 hours in that time pattern. Perfect. So I will just plug the time pattern to time pattern, and I now created my Cyclops object. It's called sunrig. Now, this particular component already gives us a preview of what this sunrig is, but it's quite small, as you can see, and we don't have access to any of the properties. So as you've seen, there's a second method, and now sunrig geometry, which I can use directly to preview and extract some of the geometry, some of the parameters from the sunrig, right? So if you're creating, for example, a diagram, this is quite helpful. It's also obviously a project and unit specific, but let's just make it slightly bigger so that once previewing the mesh, we can actually see what's happening. Perfect. So we now have our sunrig. We have 12 positions. So those would be, even though we're running here 24 hours, those sun positions would be obviously those above the horizons, right? The ones that can be drawn. The sunrig also gives us an option to display the sunrig with different projections. So, for example, I could draw it in Cartesian space or Cartesian projection, or just stick with the spherical ones. I'm sure we can talk more about the projections later when we look at some of the other analysis. So I believe now we have all the ingredients that we need. The only problem that we can, for example, skip right now is that we have this single object here being context, and we have this proposed geometry that has 3 different paths. But let's just try and see some geometry. So I will just extract one of our proposed geometries. So in this instance, this is an option 1, and we can just plug it directly into our scene. Right. So I also need a sunrig, and I also need analysis points. And I also have to flatten the objects here. So the analysis has run already. It took just 10 milliseconds, and you can see that now for each of the analysis points that we started from, we have a value, right? This is a value of this possibly sunlight hours for each of these analysis points. So let's try very quickly before we add any complexity to this. Let's just let's just build a quick visualization pipeline, so we can have our facade panels. We can just do something like a gradient. I would just use a gradient like that, and I can now use the sunlight hours results as a parameter. And just for the purposes of this, I know that this is a value somewhere between 0 and 12. So let's just set the upper value as 12, the lower value as 0. And let's try and visualize some of these panels. Right, so these are my panels. I will just graph them. I will also graph the colors. And voila, that's our that's the visualization of our sunlight hours. Okay, so let me just hide everything that's unnecessary. I will also join the mesh. This tends to be faster in Rhino for the display when the mesh is joined. So there we go. Control M to remove the preview of the mesh wires, and we have our first Cyclops analysis. Now, if you remember, we started talking about and here's the geometry that we actually take into consideration. Now, when we started talking about this analysis, we mentioned we'll run that for multiple options so that we can compare between the options and also compare the impact on the adjacent buildings of all of the options, so that we can pick the options that we want to compare in between. So hopefully this is clear. Now the way this would work is that someone would have to manually change between those options, and we can kind of see as the analysis reacts. Now, in order to run all 3 options at once, we need to make sure that as we pass our scene objects into Cyclops, we include both the proposed geometry and the context. So the easiest, and as I said, Oscar will show some of the some of simpler and scene-based methods of achieving that, but just for purposes of this, let's just use an insert item where we take each one of our proposed geometries and we insert our context, so that now if I just set this to 0, so that for each of the proposed geometries now I have both the proposed geometry group and the context, right? So in a way, we just duplicated the context so that it matches in length with the proposed geometry list. Fantastic. So now instead of just picking one of the options and plugging the context separately, I can just plug an entire tree into the analysis, and I now get the results split into a tree, right? So if you remember, we've already showed it before. Each of these branches corresponds to one of those child layers. That's fantastic. And now we will need to build a little bit more just to be able to distinguish between the options, right? So let's build something. There's again a million ways of doing that, but let's just do something like a tree statistics, so that we get access to all the paths that exist. I use the list item to pick up one of these paths, and I know it's let's say 0 to 2. Okay, perfect. So now I just very simply extract the results for one of the paths, right? So this could be a path 0, 1, and 2, right? So very standard practice again. Now I can just plug these results over here, and I also need the. It would be quite nice if I could see actually the massing that affects our adjacent buildings, right? So I can use the same path now, because I know that here at the very beginning we had a nice and clean mesh, right? So right now I'm just using the same path to pick the geometry, and I can see the preview of it as I go through my paths. That's great. Let's maybe build a little custom preview. Amazing. And I think it would be also quite good to visualize the context that we're actually running, right? So maybe let's make that in a slightly different color. Darker could work better. Amazing. And now just bring it to the front so that I know what we're visualizing. Okay, perfect. So this is already lets us preview the results for all the options that we have available. But what if we wanted to draw the relative the differences between different options, right? So let's just imagine a scenario. Maybe I will add here one more option here in the envelope, and I will call that existing. And let's just imagine that it's a kind of a low rise condition, right? We want to just understand. Maybe this is an existing site, and we want to understand what would have happened if we build something much higher, right? So now we have more paths. We have 4 paths now, and we know that our index 0 is now the existing condition. So let's copy that over so that we can compare the two, and let's say this index will always stay at 0. So this is the results of our existing condition, and now we just have to do subtraction of the results, right? So we have our active, if you like, results, so the results that we're previewing, and our existing condition. So let's say we won't be comparing existing to existing. So right now we just go from option 0 to option 2. Amazing. But here right now what we're plotting is actually the difference between the existing and proposed. So let's just do absolute so that we always shrink the difference, and we can copy our display pipeline. So the panels, those are the same panels, but instead now we will be drawing the differences. Right. Okay. So just a sanity check. We have our results. We're picking the results of the first branch, and we're subtracting the result of the existing versus the other proposed options, and we can kind of see the impact as we jump between the options. Let's okay. Let's see if we could maybe get a higher density. Okay, maybe I went a little bit too far. Okay, but this should give us an idea of how would we find this the differences in the impact between the massings. I think maybe this is a good place to pause. Oscar, is there anything you would like to add?
I mean, you can try and increase the subdivision of the time pattern just to show, because now
Right.
you're just sampling once per hour, right?
Yep. Okay, perfect. Yes, let's do that. I will just make the grid a little bit larger. So let's come back to our original grid, and now we can. I haven't actually mentioned that. So here the number of time steps per hour, right? So right now, in this period of 24 hours, we're sampling just 1 time per hour, but it could be very well. Let's say, could sample 4 times, 6 times, right? Yeah. So let's just come back. So now you can see that this gradient is a lot smoother.
Yeah.
Okay.
It's another thing on the that I thought of. This like all the objects in Cyclops where it makes sense do have both a way to visualize the geometry, like you select the geometry group, you will actually see the geometry inside the geometry group, even though it's Cyclops geometry. Same with the sun rig, and or the analysis points will also show the position and the vector in which the analysis point is pointing. So it's very easy to always kind of interrogate the model and see that you produce the right things. The scale of these is driven by the plane size preview. So if you go into the display, and there's basically a plane size preview setting there, which you might have used before. So if you change that to a higher value, it will display in a higher scale, right? So the same with the sun rig. So you don't necessarily have to create the sun rig display to display it at a larger scale. You can just kind of select the component, and it should display at the higher scale, like 5 meters radius, obviously. Yeah.
Okay, perfect. Cool. Okay, so I hope this was clear to everyone. I'm not sure if we have any specific questions, and whether, Oscar, you want to do a break now, or should we go for another one?
Yeah,
we can do another, I think, but maybe do some questions if there's any in the chat which are relevant, Ollie.
There's a few, like, quite high level, for some people at the beginning were asking, does this work in Rhino 6 and things like that. I think there's someone on a Mac that's asking, does it work in parallels or whatever it is on a Mac? Some boilerplate questions like that.
Yeah, I mean, so with Rhino 6, we haven't actually tried. I can't actually answer that. I would say you need to test, but we can't guarantee anything.
People got to experiment and see what happens.
And it's actually the same with parallels. We haven't tested with parallels, but if you have a MacBook, like an old MacBook not with an M processor, but with an NVIDIA, or not with an M GPU, but with an NVIDIA GPU, because then in parallels you would have the NVIDIA driver. So potentially, I can't, because you would be running the Windows version of Rhino as well. So
Yeah.
It might work, but as I said, we haven't tested that, so I can't guarantee.
It gets complicated, so you guys just got to test it and see what happens. We're getting
Yeah,
a lot of
and I mean,
love.
the requirement
saying,
comes from us, using NVIDIA-specific libraries to do the ray tracing and use all the RTX, like hardware acceleration and everything. And that's why we need to be in that environment.
Yeah. You're getting a lot of love. Thank you so much for sharing all the information, getting a few great comments. I mean, here's a good one. In which phase is Cyclops most impactful for you guys? Rapid concept or technical detailed design stages?
I mean, it's rapid, early stage. When you need to run a lot of options, that's often where we use it the most. That doesn't necessarily mean that it's because it's obviously extremely flexible. So you can do a very specific study of, what's the impact of this specific shading on a window, and you can subdivide the window into 1,000 panels and, exactly understand how that shading impacts. As an example, or, like I don't know, the analyses are really flexible. We try and just show in this workshop the most kind of, or some common workflows that we use, but doesn't mean that you can't use it for other things as well.
Yeah. Okay, I think that's it. Would you guys be able to save the file and then I can share it with everyone later?
Sure, absolutely.
We can try and do that. I mean, most of the information is accessible in the tutorial files that ship with the plugin,
Sure.
We can try and share these, but yeah, I would refer to those first.
Sure. Do you guys want a 10-minute break or do you want to jump into it?
I mean, we might as well take a break now. And I think this subsequent scripts will build on the same geometric setup or similar geometric setup, and we'll kind of just do a bit of changes to what type of analysis we run and which part of the setup we're actually analyzing and so on.
Okay, let's do a quick 10-ish minute break. So it's now 22 minutes past. If we're back at 32 minutes past, wherever you are in the world, let's come back online. Grab yourself a cup of tea or a beer or a coffee, depending on what time of the day it is, wherever you are. And then we'll come back in 10 minutes.
Cool.
All right, thanks, guys. I'll put you behind stage. Guys, we'll be back in 10 minutes. All right, guys, let's pick things back up. Let's bring the guys back onto stage. Oscar and Wojciech. Hope everyone grabbed a coffee, beer, cider, whiskey, coffee, wherever you are. Wherever you are in the world. Yeah, it's really great stuff. I mean, I wish I had this a few years ago. Back when I was running some scripts, would have saved me some serious time. But it's really cool that you guys have this available for people. Let me see if there's any good questions. There's one on data trees, but maybe we'll pick these up later on. I'll let you guys pick up from where you're gonna go.
Okay, then I will take over now.
All right, I'll hand it over. I'll hand it over to you guys. Guys, don't forget, in the audience, if you do have questions, put them in the comments. We'll flick through them. I'm curating them out. There's some good ones in there. We'll probably get to them at the next break or at the end. Otherwise, Oscar, I'll let you take it away.
Thank you. So I have the same files open here that Wojciech just created. So we have the context and we have the analysis file. So just to kind of go through what we have done. So we basically created our geometry inside Rhino using the layers in Rhino, and then we reference these geometries straight into Grasshopper and filter out the geometry that we need using the layer names and then splitting by sublayers. Then this is obviously a bit involved because we're running analysis on the context rather than on the actual option, because we want to know how much the option impacts the context. Sometimes I guess you would run it on the actual option, but you know, this is what we're showing here now. We then subdivide the context into little panels, and we create these points on which we measure the amount of sunlight hours. We prepare the geometry for Cyclops, and then we decide what amount of time or when in the year and at which location do we want to actually evaluate the sunlight. We run the analysis and we display the results. That's what we've done so far, and we measured the amount of sunlight hours on the facade of the context buildings. Now we are going to go a bit deeper, and we're going to use a kind of Cyclops, very bespoke Cyclops analysis called sunlight obstruction. And we're going to use it to basically evaluate which part of the option, so which part of the geometry that we're proposing for our development has the highest impact. I'll see if I can find this in the documentation. So if I go to analyze, this is a bit slow. Yeah, analyze and then sunlight obstruction. And so you can see kind of an example where we're evaluating this neighboring building, just like we're doing here, and we're basically subdividing our option into voxels, and we're seeing, okay, which voxels has the biggest impact. And this insight can then basically guide us in the direction we need to go with our massing in order to decrease the impact that we have on the neighboring buildings. Yeah, so that's what we'll set up now. Basically, these are copies of Wojciech's script. I will maybe remove what we don't need. Let's just stick with one option for this exercise. So I will go here and delete option 2, delete option 0, and delete existing. Yeah, so we'll stick with this option. Okay, we still keep the analysis context because this is still the context that we want to evaluate. Like, this is the context that we want to measure the impact upon. Okay, and then we have the static context, which we're not using to kind of analyze, but it is in the scene in such a way that it will impact the analysis. I think in this case, I guess it won't actually, because it's kind of outside of the relevant geometry, but anyway, we keep it in there. So for this analysis, we keep the envelope here. Obviously, there is only one envelope, so it's not super relevant, but we're getting the meshes, which is relevant. But now we want to voxelize this geometry, right? Because we want to basically have a way to see which part is impacting. The way the analysis works is really that you have your analysis point, you check the direction to the sun, and you see, does this travel through any of the obstruction geometries that I have in my scene. So I'll use this model extrusion that we have. Let's maybe go here. I'm gonna just hide these. Actually, we might do some cleanup here because we don't need all of this. We will need the sun rig. We will not need this analysis. Okay. And we won't be displaying any differences in this case. Okay, otherwise I think we can kind of stay here to start with. Okay, so first off with the voxelization, this can probably be done in a lot of ways in different plugins, but I'll just show a way to do this vanilla grasshopper. So we'll do a bounding box of the geometry, and we'll do it a union box. Okay, then we get the box properties. Oh, sorry. It's called deconstruct box. There you go. And we basically get the domain. So what we want to do, right, is we want to create little cubes or voxels, and we want to use the domains to basically create those voxels. So we have the domains x0 to 40, 0 to 40, 0 to 80 in Z. And then maybe in Z we can create a separate value, let's say, for a grid. So we can use a grid of 9 meters maybe for the horizontal grid. And then vertical, I guess we can do some kind of maybe a reasonable height, 4 meters. Is that a reasonable floor height? Okay. And then we divide the domains. So we want to basically split these into subdomains so that we can basically say, okay, the first voxel goes from 0 to 4, the second voxel goes from 4 to 8, and so on. So the easiest thing, or an easy way to do that, is to basically turn these into numbers. So if you plug in a domain into a number, it will basically give you the size of that domain. So if we do it for x to start with, we plug the number into A here, and because we have our horizontal grid, which is another number, we can call this division. And the total size. Okay. That basically says here that we can fit 4.4. This is just approximate, so we'll just use that. So we turn that into an integer. We probably round down to 4. We have our domain, which is there actually. Can use that as an input instead. Domain. I'm just doing this so I can then cluster this and kind of copy it for the other domains as well. So we divide our domain, and now we can see we have different domains here. Now it becomes 0 to 10. This is an approximation, so I think that's fine for now. And then we have domain output. Okay. And then I will basically cluster this. Right, so now we split the x into this amount of domains. We split the y into this amount of domains. Obviously it's square, so it'll be the same. And then we split the z, and we can use the floor height to split in z, so we get a few more domains there, 20 domains. Okay, then we basically need to match these, because now we're going to create a box from domains, right? So I'll use the initial plane as the base of those boxes, and then I basically need to match these, so I get for each box, like if I do this, x, y, and z, we just get kind of a diagonal thing. So basically we need to do a matching in order to copy them and match them around. And then we can use this quite advanced component, which is called cross-reference. And basically a holistic cross-reference, which will ensure that there is matching indices for each. So you can see here there is 0 to 10 and 0 to 10 continuously 320 times. We have 320 values for Y, and we have 320 values for Z. And now if I plug in list A, list B, and list C, I have filled my whole tower with boxes. Okay? Or my whole bounding box with boxes, rather. Then we can just use, because actually our geometry isn't that, right? It is a bit more advanced. So let's check which of these are actually inside our massing. So I take the box, I just do one of these evaluate, which will give basically the center point of the bounding box. So I get the center point of each box. I go to analysis under surface and I just check point in B reps. I plug in my points, and here, right, I have my B reps. Okay, this just gives me a boolean if it's inside or not. I can dispatch my boxes with the inside, and then if you look at the data, external selection, then you can see these are inside and these are outside, right? So we're only really interested in the boxes that are, this is like an approximation of our massing using boxes. Okay, hope that was clear. Now we basically need to turn this into something called obstruction geometry in Cyclops. So I go under Cyclops here, and then I turn it into geometry. I plug it into a geometry group here, but then I need to basically, you see there's this thing called intersection type, and this basically decides if it's target or if it's obstruction, and if it's obstruction we will basically count, we basically treat it as geometry which we want to basically count obstruction for, whereas if it's target it is geometry which will be in the way, but it will not be transparent in such a way that a sun ray will not be able to travel through it, and we won't be checking how much it actually impacts the analysis results. Okay, let's call this voxels. There we go, and then this is now set to target, but for every one of these kind of enum inputs, you can always right-click the component and click generate missing enum inputs, and that will basically give you the relevant enum. And here I can now change this to obstruction. You can do this in different ways. There is also the enum component, and this one basically lets you right-click and choose which type of enum you want to create. But that's obviously, it takes a bit more time, so it's very neat just to generate missing enum here. Okay, so that's the geometry group for the voxels. We have the geometry group already for our context. Now we just need to make sure that the context is actually target intersection type, right? We won't be using the proposed geometry because that would obviously be in the way then of our voxels. So I will basically just remove that, and we don't really want this stuff actually. Okay, sorry, I'll keep the context one, but I remove this, and we can copy this group. Can we do that? Yeah. And we can name that voxels. Okay, and we plug in the geometry group with the voxels there. We don't want to see that geometry group. And we want to group the thing that voxelizes. Okay, seems like I have black instead of white. Let's just make it white instead. Cool, and group that. Okay, so we created our voxels. I will actually delete this because we don't need it. And we don't need this mesh. Still need our context as we said. Okay, so now we go in here and we look at the sunlight obstruction analysis. Very similar to the sunlight analysis. Pretty much exactly the same inputs. So we then want the geometry group with the voxels and the geometry group with the context to be in the scene when we run the analysis. So that is what we plug into the scene objects, right? Then we have the sun rig, which we already created. So I'm just reusing what Wojciech did before. Plug it into sun rig. We have the analysis points, and we have to remember now that the analysis points are obviously from where we check the impact of the geometry, right? We check how much does each of the voxels shade sunlight towards these analysis points. So we will, even though we plug in a list of analysis points, we will get results relating to each voxel, right? We will know for each voxel how many sunlight hours it obstructs, not how many sunlight hours per analysis point necessarily. So that runs. Wojciech likes to put in a toggle here. Usually you don't need to, because usually the analysis is not actually the thing that takes the most time in the script, but as safety we can do that. Okay, and then you see we just get one object, sunlight obstruction result. And that is because these results are a little bit more complicated, so it's a bit hard to just flush them out in a data tree or in a list. So instead, when we get an object like this, we need to use the component called filter results up here. So I'll drop that, and you can right click this and choose sunlight obstruction result. This is because in other versions of the plugin, there is more types of these results. But anyway, if I plug in now sunlight obstruction results here, you can see that it kind of changes. And now it allows me to basically choose which geometry group do I want to get the sunlight obstruction results for. Right, so I created one geometry group up here with the voxels called voxels. But I could have another geometry group in the scene as well, measure the obstruction for that geometry group, and that way I can basically filter using this component which geometry group do I want the results for. But obviously now there's only one, so if I click add here, this works similarly to the enum. It will create that input. And you can see in this drop-down, voxels is the only option I can choose from. And now the output will be the amount of hours total that each voxel obstructs sunlight hours. Okay, just to sanity check 240 voxels, and it will be in the order that the list is obviously plugged in here. Right, for the first geometry here, you will have the first result here. Okay. And let's reuse some of Wojciech's analysis here, or display rather. We can just get the bounds here just to see. So the maximum is 80. I'll just plug in an 80 then to the upper limit. Okay, we're not going to do it per option here. Okay, so we plug in that, and then we're getting 240 colors, right? Because we have 240 voxels. And now we don't really want to display this on the facade. We want to display this on the voxels, which we have up here. So we pull those down, and we plug those in here. And then we turn this off. And now we can see the voxels, right? And we can see basically, which is, I guess, naturally the ones that are kind of closest to the facades have the highest impact. If I preview this, you kind of get the sun rig in relation to that, and you can see that. Obviously, if the sun is coming from here, these geometries won't really shade much, because the sun that goes through those geometries will just hit the ground, while the geometries up here obviously shade like this geometry, right? It shades probably for the facade behind there from this sun position, but it also shades the facade here from this sun position, right? So they have a big impact, the ones that are white here. But actually, maybe it makes sense to just create the preset, which is green to red. Okay. Then as a little, I don't know, as a little filter here, you could maybe have a specific GFA that you're kind of allowed to build, as an example. So then we could maybe do a sort and we could sort our voxels, right, by the score that the voxel has. And then we know that the voxel here is now 9. We can actually take that number down. Right, so let's put bifocals doesn't update that when you update the name of the parameter. Anyway, I'll put that here. I'll take that out. Okay. So we know that each voxel is 9 meters. So maybe if I multiply 9 by 9, that's the area of the voxel, right? 81. And then let's say that we're doing, I'll just put in 1,000 here to start with. So we can divide let's say this is total GFA. Or we can call it, just call it area actually. Okay, so let's say we're allowed to have 1,000 square meters of voxels. We divide it by 89, that says that we're only allowed 12. That doesn't make sense. So I'm gonna say 10,000 instead. Then we're allowed 123, that makes more sense. Okay, so then we split this list, right? So we have our voxels, and we obviously want to keep the ones that have, or in this case at least, we want to keep the ones that have the lowest impact and remove the ones that have the highest impact. And we want to reach a GFA of approximately 10,000 square meters, meaning that we need 123 voxels. So we split this list at that number. Okay, and if we actually then just plug those, oh sorry, I plugged in the keys. We obviously want the values because they are the voxels, and they are already colored. So we just plug that in there. We preview off from this, preview off from this. We actually want list A, right, because we want the ones below. There we go. Maybe I can set this to 20, sorry. Okay. Now we can kind of filter out how many voxels we want to be displaying or want to use. Obviously, it creates a bit of a gap, so this, as we've said before, is just kind of a guidance on how many voxels you should use. We can see what happens then if we, just as a test, if I create a time pattern again. Instead of doing it for a specific day, maybe I want to check just the whole year. That will obviously create a sum position for the whole year, right? And now 80 doesn't make sense. Let's get the bounds again just to see what the max is, 21,000. Actually, I'm just gonna deconstruct that domain and just make the display dynamic. Okay. So now we're using the impact of the whole year instead. Creates a bit of a funny look here, but that's usually the case. This is guidance, as I said. Okay, I hope that was clear. I can also divide this into something smaller just to show some more performance. So now still the analysis runs on my laptop here with an A4000 GPU, I think, for 2,600 voxels and 4,400 sunlight hours, 2,300 points that we're checking against. Yeah, I hope that was kind of clear. Let's see if there's any concepts we can maybe talk about. So We talked about those, we talked about that. So there's one thing called custom data and get property value, which can be quite interesting. So on each Cyclops object, we basically attach a dictionary that can hold custom data. And that allows you to basically send information with Cyclops objects. Then we also, I mean, it's similar to what's now been introduced in Rhino, where you can kind of apply key value pairs if you use that. And you can in Rhino also filter by key value pairs, but yeah. You can use that to basically get and set custom data on an object. So if I put this here, you can see I input a Cyclops object, which is, for example, my geometry group, right? And I say the name of the key. What can we attach here? Okay, I'll just do something random. Let's just attach my surface. Okay, that's the name. I'll create a simple surface here just to get some geometry. Okay, that's the surface. I attach the value. And then I can also create the description, which is called my surface that I attached. Nice. Okay, that's the description. I still have the same Cyclops object, but now somewhere else in the script, I can then get this data. And I can get it through the get property value. And this component not only exposes all the data that's in the Cyclops custom data dictionary, it also exposes all the public properties of that class or of that object. So if I drop this and I plug in my object here, which was my geometry group, right? I click add to basically then again generate an input dropdown. And now you'll be able to see all the, first off, all the properties of the geometry group, right? So you can see every geometry group has a GUID, and then we have the name, the actual geometry, the transforms that we inputted, the visibility masks, the intersection type, and my surface. Sorry, that was outside the screen, I realize. The name, the geometry, the transforms, the visibility mask, intersection type, and my surface. And you can even see that the description that I input here, you get when you hover over my surface here. But yeah, so as an example, right, if I want to actually get the geometries, like instead of pushing all the voxels later in the script, I might already have my geometry group later in the script. Right, so instead of feeding a lot of kind of wires around in the canvas, I can just take my geometry group here instead. I can get my geometries, right? This will output the Cyclops geometry. I can get the geometry. This is maybe not the most kind of efficient way to do this, or the best example of where this is useful, but still this is kind of a way to retrieve the data that you have inputted somewhere else in the script. So here I now have my meshes for my voxels, right? And if I flatten this, I can obviously use it here. Preview. And I get the same thing. And I didn't need to output the boxes up here. Okay, we'll wait a little bit with the scenes. Let's see if there's anything down here which would be good to go through. So yeah, we can go through the time patterns. So there's quite a few ways to create these, and quite a few more ways of creating time patterns will be released in the next version. But by default, it creates sampling within the hour. Does that make sense? So what you see here, when we just have this one is not the one we're displaying this one, right? here we have a sampling of once per hour, meaning that if you want to evaluate how many hours you're getting sunlight between, like between 12 and 2, let's say, right? You need to have 2 samples because you have 2 hours that you're covering between 12 and 2. So then we sample at 12:30 and 1:30, right? It wouldn't really make sense to sample at 12 and 1 because that would not be an accurate representation of the time that is between 12 and 2. Does that make sense? So that's why you're seeing these samples every half an hour. And if we just go back to the 1 day here, you can see that when we go from 0, or 1 obviously is the minimum value, where we're at the half hour. If you go 2, you get at the 15 minutes, right? And so on. Or sorry, 3 at the 15 minutes. This is also quite well documented inside the documentation. I can go in here and objects. You can see here we also describe kind of this sampling and how it works, and also how the different ways of creating time patterns work. Okay, I think we're kind of finished here, and we can jump into some radiation.
I think, Oscar, if you want to do the scene now, because we will have to use it in the radiation. I can go for it as well, but
okay,
since
no, sure, I
you're
can
describing some of this, yeah, do that.
Yeah. Okay, so in this, it's almost better to do it actually in the previous script.
Mm-hmm.
Don't you think? I will save this and save this. Sorry, I'm working from a server, so it's a little bit slow. Or it's very slow. Maybe it's the streaming that takes all the time. There we go. Okay, file. We go back to the sunlight. And here we go back to the sunlight. Okay, so now we're back in the sunlight hour script. And as Wojciech did before, he basically created a branch for each option, and then he inserts the context, right? Because this runs by branch. So for each branch, we run an analysis, and each time we basically upload all the geometry to the GPU, we run the analysis, and then we remove everything. And then we create, so we create a new scene, we upload the geometry, we delete the scene. We create a new scene, we upload the geometry, we delete the scene. That's what happens when you don't input anything in the scene input, right? So for every time, we basically rerun this process on the GPU. Now, the context, right, that stays the same for all of these analyses. That doesn't change. Obviously, in this case, we just have 9 little boxes, so we don't really see any difference. But in some cases, you have an extremely complex context, so you can have gigabytes of data in your context model if you're running kind of a city scale analysis. But if you're just changing the little massing or whatever your design is, you obviously don't want to keep on uploading and removing those gigabytes of geometry on the GPU every time. And basically for that efficiency is the reason that we introduced something we call the scene. And the scene, you basically create one by dropping the scene component on the canvas, okay? And this is now created basically a static state on the GPU onto which we can add things, remove things, and run analysis, okay? And then I can use an add object onto the scene. So I take the scene, and now what is static, right, is my context, so I plug that in here. So now I have a scene that contains only the context. And now I can run analysis on the scene, and I don't really need to then input the context again to that scene, right? So I basically delete this component, and then I will plug in the proposed geometry in my scene objects and the scene into the scene. Okay. It sounds maybe very clear. I hope so. It can get very complicated.
Maybe
Yeah.
Oscar, you can also just show how is that in the same scene we can run multiple geometry groups and kind of how that relates to their names.
Yeah. So what Wojciech was pointing out before, it's very important to name your geometry groups, because now instead of removing the scene between each analysis, we're actually keeping the same scene. We're just kind of updating we're basically adding new scene objects, right? So for each branch here, we keep the scene static, and when we run the first branch, we add the things in the first branch to the scene, we run the analysis. And the things in the first branch will stay in the scene forever if they're not replaced or removed, right? So because we're creating here 4 different geometry groups, they all have the same name, and the name, as Wojciech said, is the unique identifier, right? So if you add a new geometry group to a scene which has the same name as one that already exists, it will replace it. So that's why this component still produces exactly the same results, even though, because we basically have a scene, we add one option to it, and then we add another option, but because it has the same name, we remove the previous one. You can obviously then also use the scene for something completely different. Like if you're running other types of analyses, right? You again can reuse the scene for for something else. But I think we get a bit more involved in that in the common scripts. Because then we start adding materials and so on, which gets a bit more involved. Okay, are you happy,
Okay.
Wojciech?
Cool, I am happy now. Thanks, Oscar. Okay.
Any questions, Oliver, we should pick up before we jump on to the next setup?
There was no. I think everyone's kind of digesting what you guys are doing. It's all really good. I mean, someone was sort of asking in the voxel example, can, you know, I guess that you just make a new script, but can the voxels grow rather than subtract? But I guess it's just like totally based on how you make the script.
So if the voxels can be both occluders and sensors.
Yeah.
Uh,
Which I guess in theory is possible.
So this is the example that we would normally run in a loop. I don't know if Oscar, you want to talk about it, but basically at each iteration stage, you would have to be adding just one voxel.
Right.
Yes, we've done a few analyses like this before, where you kind of step in a way you run one. See if I don't have that open anymore, but you basically create one voxel, and then you evaluate, and then you make that opaque, right? It's not transparent anymore, and then you check, okay, of all the voxels that are on the same plane or possible to add, just stepping upwards, where should I add a new voxel in order to increase the obstruction?
Yeah.
But not, I don't know, it's very hard to actually explain this this workflow, but there is iterative ways to kind of add voxels, make them because the problem here is that the voxels they are transparent, right? So a sun ray will affect all the voxels that it travels through.
Yeah.
And that's why we're getting these kind of strange shapes, and sometimes because there might be a voxel in the center that impacts the most because it sits in such a way that sunlight from a lot of directions travel through it. It doesn't mean that removing that voxel will remove the impact, because there might be other voxels that also shade the same sunlight, if that makes sense.
But it's a rabbit hole some people can go down and test.
Yeah, it is.
But it's possible.
Yeah, it is.
All right, I'll let you guys continue.
Okay, Wojciech, you take over a bit.
Perfect. Yeah. Okay. I'll share the screen again, and we back. Okay, perfect. So I will once again come back to the. I think this is generally a good basis since we covered a lot of the kind of rudimentary stuff. So I will again come back to the sunlight hours script, but now I will save it as an radiation script. So we will just modify this rather than starting from scratch. So I think again we can remove the option analysis. We can remove the instruction that was previously the sunlight hours. And now we will also try and showcase a little bit of this interactive or real-time aspect with slightly more complex context. We'll get to that in a second. But maybe for now, let's just create a new layer. I will just call it interactive geometry, just so we can keep this model nice and simple. And I will just for now start with a simple box. Okay. So let's make some changes here. First thing, we're not gonna need any of that, and the square model can also go. Instead, we'll just do interactive geo, and I should now have access to my geometry, and you can see that as I move it, it responds immediately. So what else do we need? Maybe to start with the radiation analysis, we will run the direct cumulative radiation. So it relates to the irradiance received by a point or a number of points, in our case from the sky. We will focus, as I said, on the direct radiation that measures the amount received from a sky during a specific period. As we showed in the previous example, during the presentation, this is something that could be helpful in a lot of different scenarios, in urban scale and facade scale, early or later design stages. Okay, so let's see actually what do we need. Perhaps a good way to start would be to now bring up the actual analysis and see what we need. So radiation analysis, again, we're looking at the cumulative radiation. So radiation measured for a series of times, series of dates, but we can be also measured for point in time. Okay, but let's just stick with the cumulative radiation. And okay, we can see that this component looks different to the previous ones in the sense that it has much less inputs. Because it relies on something called shading mask. Now, we'll talk about the shading mask in a sec, but let's bring it up first. Okay, so this looks a lot more familiar to what we've already seen. And shading mask is a type of analysis that is used to create the shading masks that are then used by other analysis, like radiation or daylight, for example, we'll see. And the shading mask describes the relationship within the scene, right? We now know what the scene is, between the analysis point and the hemisphere using shadow factors. So let's maybe look at the documentation again. Just bring it up here. Okay, so the definitions are here, but when it comes to diagrams, I think maybe good looking at some of this. So we have a selected analysis point, one of many points that we're testing against, and the result of this shading mask is, or the shading factor is a multiplier for how much of in our case, the radiative energy from a specific cell in a hemisphere will impact the analysis point, right? So depending on the context and later also the materials that Oscar will be talking about, we will get for each of the points, we'll get this kind of a map. It's a projection of the sky hemisphere where each cell is colored depending on the impact that each one of the patches have. Now we haven't yet talked about the hemisphere, so let's do that now, so that we can understand this slightly better. I will also remove now the sun rig, and let's start by creating a hemisphere. So hemisphere is one of the objects here in Cyclops, found under objects. And we, again, similar to Sunrig, we have two ways of creating it. We have the hemisphere and hemisphere mesh. Let's start with the hemisphere. And now, as I said, we can, depending on the size of the plane, we can see its representation. Maybe just to make it a bit easier for us, I will immediately also bring up the hemisphere mesh so that we can scale it. We could do that with the plane, but because we're working with quite a big model, I just find it easier to scale this way. Okay, amazing. Okay, so the hemisphere describes the subdivision of the dome into discrete patches, and it requires us to define a cell count and the type of subdivision. So for the cell count, it's just a target number of cells that the dome should be subdivided into. And then the subdivision is, again, an enumerator. Quite common in environmental analysis is using the Reinhardt-Treganza sky division. So if we're interested in what any of that means, we can again go into the documentation. So in this instance, let's just go to the documentation here. Hemisphere. Okay, perfect. And where are we? So for example, the Reinhardt Treganza is a standard, as I said, is based on the subdivision of 145 cells, right? But there are also others depending on our use case, and you're welcome to come in here and read about the differences and advantages of using any of those. For the cell counts, let's just use the 145 to start with, and this let's just create the hemisphere. Now we can talk about the visualization of different parameters maybe in a second, but for now let's just plug our hemisphere into the shading mask analysis. We then need to define our weather data, right? So this is something you would be familiar with from Radiance. We'll be using here an EPW file for London. I just prepared here on the side my local path, but it would be something that you would just download like for any other analysis. For example, here in the Ladybug tools, if you following along, you could just go to ladybug.tools/EPW map, and depending on the location, you could find some of these weather sets that you can use to extract the radiation data. Okay, so here's our hemisphere. Now, to create, so as I said, we in order to calculate this radiation, we need to create an instance of the sky. We're gonna create the sky series, since we're looking at the cumulative calculation. So first thing, we need to create a weather object. A weather object contains the data about the environmental conditions at the specific location, right? So we have a component called weather, and we'll get away just by plugging the path that already creates the weather object. As Oscar said, if you're interested in kind of what's inside, you can always use the Cyclops get property and look at some of the properties that are created once this object ingests our EPW data. Okay, so next we need the sky series. So now, what is sky series? It's it contains both the cumulative and over the time data about the energy emitted from the sky at the specific location at specific time period. It's used for radiation and daylight related or analysis related to daylight and radiation. It's usually also used in combination with the shading mask. Okay, so if we plug now the weather and the hemisphere, okay, we can see that we also have an input missing, and it's a time pattern that's missing, right? So similarly to the previous example, we get again time pattern. We do it from schedule, but this time instead of specific point in time, we will have to define a series of, or actually previously we were defining the series, but for just one date, we just had a series of hours, right? So let's just do it for, we're gonna do it for entire year. So maybe actually a better method is this full year time pattern. So this is something just recently added to Cyclops. So previously we would have to define, 1 to 12 months over 24 hours, but the full year gives us a time pattern for entire year. I believe it's going to be 8,760 hours. So perfect. We can just do this. And I think we're now good to go. So maybe what Oscar mentioned about the scene, we will build a quick scene. So let's call this scene a radiation. Okay, and we will add objects to the scene. So in our instance, we want the context, which, to remind, is this geometry over here. So we're going to add the scene objects. We're going to plug the scene to our shading mask, and we're going to, as a scene object, we're going to just use our interactive geometry, right? So I haven't really prepared it yet, but let's call that active geometry. Okay, so just so we remember, it's now a Cyclops mesh active geometry, and we can plug it now into our scene object. And as I said, it's just as a part of the habit. Let's just have this Boolean switch here. We obviously also need the analysis points. Perfect. With the only difference that I am still using as previously the sampling on the context, but this time we will be running the radiation actually on our active geometry. So let me just disconnect the sampling of the facade from the context and instead plug our mesh, right? So now you can see we're sampling the mesh, and we have our analysis points here on the interactive geometry. So as I change the geometry, the process reruns. Okay, so let's see. So here is our shading mask, and perhaps we can see how would one visualize the shading mask maybe in a second. But first, let's just try and fill the rest. So for the radiation analysis, we're going to need the shading masks. So again, you would expect here as many shading masks as you have analysis points. We had 646, and the sky series can be directly plugged. Let's in a second visualize what those shading masks mean. But for now, just to finish this part, let's visualize the cumulative radiation. So again, the analysis pipeline is quite simple, or the visualization pipeline is quite simple. We just take the panels, and we can directly just plug them as they are. But actually, the parameters that we visualize by will be something like bounce from the domain, start, and we end. But now let's use something appropriate for radiation. So we obviously have it reversed now, so we want actually the red to be where the radiation is high. So I would just to make it simple, I would just reverse the start, right? So we have our domain ranging from 400 to about 1,000 kilowatt hours per square meter, and we visualize it quite easily. Okay, perfect. As I mentioned, right now this analysis is quite fast, but one could say, oh, but obviously your context model is quite simple, so it's not that impressive. So I think maybe the next step would be just to show how would analysis like that work on with a much more complex context model, and I prepared here a path to the slightly more complex model. It's a kind of imagined quote from New York. So here I have the model just as a Rhino file that I can directly input in Grasshopper, just so that we can see how the model like that would perform with more complex context. Okay, so let's just try to build it very quickly. I can just import the 3DM file. Oops. See what happened here. Okay, we're back. So you can see it's a lot more geometry. Now I can hide maybe the geometry I won't be using, and I can see my kind of imaginary building is standing somewhere in the middle. So it's a good habit to have, just to use the get clean mesh component that we started with. This model is not really or might not be very clean. There was a lot of meshes cut and removed, so there might be some zero area triangles and so on. So for the purposes of this exercise, I can just ignore the warning for some missing or invalid meshes, and instead I can just join the mesh. Okay, so let's visualize it and just use it as it is. Right now, it's a fairly big mesh. It's a 400,000 faces, just slightly over that. So let's see how our models will perform now. We know that if we inputting a large and complex context, we only have to do it once because we're taking advantage of this add object and scene method, right? So let's start with that. I will obviously need to pass it here. So instead of using our reference context, we can just maybe visualize right away, and I will just pause the analysis. So yes. So if I now plug the geometry directly, okay, we can see that the geometry is now in the document, and it's already probably here in the scene. It is added here. It is added here to the scene. It took just 90 milliseconds, and now I can run the same analysis. But right now, instead of dealing with this very simple context, I have this quite a large model, and I can very quickly start manipulating this geometry. And as I manipulate it, I see it responds in real time. And to make it, maybe not so meaningful for the analysis, but just for demonstrative purposes, I prepared here a little example where we would, let's say, just for the, if you're following along, don't feel like you have to do this, because this is just as a quick demonstration. I just want to show that we could potentially take this kind of already large model. We could again use the domain, just to understand what is the size of our bounding box, and now we can copy it a couple more times. So if I just take one of these components, so rectangular grid of this size, And maybe not, let's not go too far, but if we just have 16 of those, that should give us some preview. So now I could just use move component and use the flatten points, right? So I would expect now the copying actually takes a little bit of time, but let's see if we can get this geometry in. Okay, so it will be obviously much better if I join this mesh. And then I have actually realized that the reason why it's taking quite a lot of time is because I'm using this custom preview component, which it would be much better if I just used, I think, mesh color. Okay. Okay. So here we go. Let's see what happens. I might have gone a little bit too far with the 16 versions of it, but let's see. Okay, perfect. So you can see that now it took quite a bit longer, but the geometry is now in the scene, and maybe we can preview it. Oh, I'm producing, so okay, so this is my bad because I joined the mesh. It's actually invalid, so I might have to just send them separately. Apologies. Yeah, okay, perfect. So now, since we just visualizing the mesh colors, we cannot obviously see the shading right away, but you can see that the okay. I might be doing something wrong here. Just 1 second, just to debug this. The mesh that seems to, I'm not sure if this is something to do with how this mesh gets mutated after it's moved, but once it's moved, it seems to be made invalid. Just give it another try, but if it won't work, then yeah, okay. I'm not too sure why on this multiplication the mesh gets broken for this fragment of the city. But let's just, for the purposes of this exercise, stick with the mesh here, and the preview that on the once running this radiation, even with the, so this is about 400,000 meshes, the model still remains smooth. I don't know if there's anything else that we could show here, Oscar. I could potentially go through the shading mask visualization, unless you want to go through this with your next example.
I think on your test there, just as a quick test, see if you can plug in your invalid mesh into the get clean mesh component, just to see what happens.
Yeah. Yeah, let's just make it a bit smaller, just to see what's going on.
It might take a bit of time now because it's trying to clean up the mesh. So let's see. I don't know. Maybe it doesn't work.
There we go. Okay, perfect. Thanks, Oscar. That's great. Cool. So let's see what if we can just run this analysis, and there we go. Okay, so you can see I kind of added the model kind of towards the positive coordinates, but you can see that now instead of loading this 400,000 meshes, we're actually loading that times 8, or 9. So you do the math, but it's somewhere in the region of 4 million faces. And if we were now to modify our geometry, obviously the preview of the mesh that we're displaying takes some time, but we're still going to get a fairly impressive results. But we'd actually have to measure, as in the Oscar's previous example in the presentation, how long is the actual analysis and how long is the actual display pipeline, because you can see that the shading mask and the radiation takes just 150 milliseconds or so. Cool.
I guess you can briefly talk about the fact that you can actually input the transform straight to the geometry group instead.
Okay, right. Yeah. So the geometry group component also have this idea of the transforms. So you can see that here I really wanted just to show how do we copy the geometry, just to show how much of it can we actually input. But quite often, if we're dealing with something like trees or cars or buildings that are just being repeated, similarly, like in rendering, we use instances. So we could in Cyclops. So right now, if we just came back to the previous example, we could actually, I believe, we could actually use the same points, but instead now of moving the actual geometry, we could use this transform list to actually transform the context directly in the geometry group. And that process would then be much faster. And we could, again, the preview of the mesh will take most time, but you can see that in case you have some repetitive geometry, you can just make use of this transforms, which is in intuitive way exactly like instancing of geometry in your rendering software, like a Vue.
If you use Rhino a lot, you can very much see the geometry group as a block, right? If you create a block, you copy the block around, you're not going to create new geometry, you just create another instance with the transform.
Yep. Okay.
I guess if you just look at the sampling settings that you have as an input there.
Oh, absolutely, yes. That's here. Okay, so let's do that. So the sampling, and maybe we will talk actually a lot more about sampling in during the daylight analysis. But the short story is that the sampling setting control how many rays should be cast and when they should terminate. In here, actually, the intention has been to only calculate the direct rays, so we're not actually taking into consideration any bounces. Okay, so the number here of the sample specifies the side length of the grid within the randomly sampled rays that are cast, right? So if we, for example, plug here 100, the actual number of samples will be, or the actual number of rays casted will be 10,000. In this instance, we're only interested in the direct irradiance, so we don't really care if or we shouldn't really set the bounces, as we're not really interested in the interaction between, for example, the materials and their properties or the transparency of objects. Yeah.
Yeah.
Cool.
Okay. Cool. Any questions we should pick up?
Yeah, there's not so many questions, like compliments. People are saying this is going to be super useful, particularly on massive urban projects. people are going to be jumping into this over the weekend. A lot of compliments. Do you guys want a little break, or do you have one more that you'll
I mean,
share?
we can take. We have an hour and 20 minutes left. I think we can probably afford another break if.
Sure, we can do another little break.
Maybe 5 minutes enough for me, or
Yeah.
Do you want to do 10? Let's do 10. I don't know.
Let's do 5. We'll do 5 minutes. It's 5:42 here, so we're back at 5:47. Does that sound good?
Sounds good.
That's good.
All right. I'll put a 10-minute break sign up, but it'll be 5 minutes, guys. Okay. All right. We'll see you in a bit. All right, guys, let's pick it back up. I'll bring the guys back for the home straight.
Cool.
Welcome back, guys. Thank you so much. It's really interesting stuff. Actually, it's like it would, like I keep saying, it would have been mega useful a few years ago when I was doing these giant projects. Yeah, it's really cool stuff.
Good. Sorry, I'm just getting prepared here for the next session.
I think the user object stuff is quite interesting. Like I came from the world of using Edelfront to fabricate stuff and things like that. So it's quite cool that that's now part of this. So you could kind of, I don't know, embed all this information in the geometry as well. It's really powerful.
I mean, it's kind of just an extrapolation of object-based programming, right? What you do is you pass around objects on the canvas.
Yeah.
So you might as well utilize that kind of functionality. It's quite interesting because it's quite generic. So if I look at the get property value, right, I can just create like a point here. And if I plug in a point to this and click add, it also exposes all the properties of like a Rhino object. I haven't tested with many other plugins, but you might be able to just plug in other objects from other plugins as well and use this to kind of get a specific value.
Yeah. I'm sure it probably work, yeah.
It's quite efficient because otherwise you need specific components. Like obviously it creates a few more components on the canvas, but you need otherwise very specific components to deconstruct specific objects. Whereas in this way you kind of get the values from just single object.
Nice. All right, guys. I'll let you guys take it from here.
Yeah. Okay.
The home run.
So now we will jump into some daylight. It will get a little bit more complicated. I'm just setting up my screens here. Because now we start talking about sampling even more and materials and some things like that. But I'm here again starting from the script that Wojciech had. We might as well keep this context, I think. There's no point in going back to the boring old cubes. But we can maybe remove this unnecessary copy that was just for illustration. So I'll remove that. I'll remove this display because I think Wojciech already created a display down here. Okay, and I don't remember what shortcut he had for this. So Control M, preview mesh edges. You don't need to do that. Okay, this was a bit dark. So let's see. Okay, so we have the interactive geometry. Now we're going to run a daylight analysis. I'm going to run it on kind of a floor plate. So we're going to use a horizontal subdivision instead of a vertical. We're keeping this. Actually, we can just delete these layers. Yes to all. We don't need this stuff anymore. We don't really like this is Wojciech said before. This join is really just because it's visualization in Rhino and from Grasshopper into Rhino is always much faster when you have fewer instances of meshes. So it can be quite efficient to join them. Okay, so we have the context and we have our interactive geometry. Now let's start with creating some kind of, I don't know, I mean some kind of floor plate here. Right? Okay. So first, we basically will want to create windows on the facade of this. So I'll take the, let's see, how should we do this? Okay, we can create a floor that we can kind of move up and down. Maybe that's the easiest actually. Okay, I'll just create a bounding box here. This thing, that's my geometry, right? Maybe I'll just move all of this stuff down a bit because now they're working in the top here. Okay. Create the bounding box, and then we deconstruct that box. Okay, we get the said properties of that, and we'll basically try and divide this into floor plate, to floor, to floors. Okay, so we plug this in here. I will say our floor again is 4 meters high. Division, so we divide the said number by 4. Means that we want sorry, in this case you apparently have to put it through a number before you divide. Okay, so we have our segments there. These are the potential floor plate geometries. Okay, let's get a list item. That, okay, and we have 28, so let's just do, let's just put it 10. Wojciech always does this with very neat writing. I don't. Okay, so now we can kind of pick which floor we want to use. Is the plan anyway. Okay, and then we can deconstruct the domain. So we deconstruct this domain, and then I create an XY plane at the Z. Okay, so I turn start into Z, I turn end into Z, and then I just create the plane. Okay. There might be a million easier ways to do this. I'm just kind of trying to set up a simple floor plate here. Okay. And then we intersect the plane with the mesh. Sorry, that was point cloud. Very similar. Okay, so now I can choose my floor plate. So I'm just going to set this over so I'm just going to okay, so I can now pick the floor plate here. Nice. And then we take just item these curves and flatten that output. So because we have the start first, we have the lower curve first. Okay. I'm not gonna really create any complex walls or anything inside. I think we just kind of subdivide the facade and then create a floor and a ceiling. Okay, so let's do boundary surface first. That will be our floor and our ceiling. Okay, and actually from that we can just get the floor here, and then we can we'll basically turn it into a mesh, and then we'll use the center point of the mesh faces as our analysis points. Okay, so basically similar like before. And actually I can probably copy this, right? I plug in my surface here. I say how big do I want the voxels to be. Right, here it's 4 and 4 meters. Let's do 1 and 1. Let's see what we get. That will give us 2025 samples. Okay. Actually, I'm gonna go in here, hide that, preview off. preview on Control M. It was, yeah, Control M. Okay. Zoom into that. So that's kind of our analysis points. Here is again, if we're going to use this surfaces as our ceiling and our floor. Actually, let me do this. If we're going to use these surfaces as our ceiling and our floor, then we need to move our, sorry, I'm just hiding the grid as well. We need to move, obviously, the analysis points, right? This mesh, just like Wojciech said about the facade, we need to move this up a little bit so that it doesn't intersect with the bottom. Is there an overhang? Yes, that's not what I want. You see that this mesh is not actually exactly on the surface edge. Maybe it's because we have a V count and a U count. Or no, probably not. Someone might be able to answer why this happens in the comments. Anyway, so we have our analysis points, and then we want to move this, or we have our mesh, sorry, and we want to move this slightly instead. I think depending on the daylight analysis that you're running, you obviously want to do it at different heights, right? If you're doing whatever certification, you might be a requirement of the height. I'm just going to do it 0.1 meters above the floor. Okay. So we have moved that up, good. And then we can use the same component here again to basically split that into faces and turn those faces into analysis points. Okay, so I'll just copy these two groups. Good, and we have the geometry there. We're getting our vertices, we're getting our mesh faces as separate meshes, we're getting analysis points in the center of each face, and we get the panels to display the results. Okay, we can group this, add that to the group. Okay. Then we need to create some kind of facade. And let's do this. Let's explode this curve. I'm just gonna do this super simply. Okay, maybe is this gonna help us maybe? Yes. Okay, so we have our segments. I'm just gonna divide curve. We can plug in just a number there so we can control that. 100 is not reasonable. Okay, create the polyline out of these. Okay, this gives us a polyline, and then we explode that polyline to get the segments. And basically what I'm going to do now is I'm going to do basically every other one a window and every other one opaque. Okay. So what we can do first is loft this, and we have, yeah, let's simplify. Okay, so we have first 0 and 1, which is obviously the bottom and the top curve, and then we have 0, 1, 2, 3, 4. Why do we have 0, 1, 2, 3, 4? Okay, instead of intersecting the mesh, I'm gonna intersect the VRAM. Now we hopefully get a cleaner curve. Yes. And now we only have 0, 1, 2, 3. Because I was a bit confused there that we had 5 segments. Now we have 4 segments. Okay. Create the polyline. We have the segments there per polyline. And now if I use the shift, right? So divide that here. Okay. Now we have basically 2 lists with 76 segments in each, right? The segments for the bottom and the segments for the top. I can use flip matrix here. So now we have instead 76 branches and 2 lines in each, and we just loft these. Okay. So here we have our panels. And then I flatten this, not reverse. And then I'm gonna code pattern on this. And plug in a toggle and a toggle. And a merge. Okay, so now we're gonna get this pattern of every other. And then we can do a not on that. Basically reverses the booleans. Run this again. Right, so then we get the ones above. And so we'll use one of these to basically apply glazing material. We use one of these to apply an opaque material, and then we get a closed facade. Okay. And we have our floor and our ceiling. We have that. What else do we need? Okay, first off, we don't need to subdivide the facade. We can just delete all of this just to kind of simplify it and clean up the script a bit. Let's rename this one to floor panels. So what else do we need? We're gonna need the kind of tower geometry, right? The option geometry that that is not within, like we don't want to cover the opaque floor plate. We don't want to cover the facade of the floor. Okay, we have these. This is the outline of our floor plate. We don't want to have this geometry in the scene, but we want to have the geometry above that floor plate and below that floor plate. And I guess a quick and dirty way to do that is to do should we do this clean? No. Let's do it dirty. Trim solid. Okay. That's not what you should be using usually, but I'm going to use it here. So that's my shape. I'm going to create just see if this works. Bounding box on these curves. There we go. That's the geometry above and below, which we still want to keep in the scene, obviously, because a ray might bounce on a neighboring building and then bounce on this facade and then go into the sky. As an example. So preview off, and now we have to start thinking. Okay, this we don't need. Now we have to start thinking what should have what material, right? What should be dark, what should be bright, what should be transparent, and so on. So first off, for the context, we can create a new material. So I just write material here. Okay, and now this is quite similar to the radiance materials, right? So there is plastic, metal, mirror, glass. There's also volumetric, which we maybe don't in radiance, and emissive, which we don't have in radiance. But these 4 are very similar to what you have in radiance. And if you've used Ladybug tools, this is maybe what you're used to. There's also material from radiance, and this takes a string, like a radiance material string, right? A radiance material is described by a string, basically. and converts it into a Cyclops material. So if you already have a workflow which uses radiance and that material definition, you can convert it very easily into Cyclops. Okay, but I will create a new material here, and we will create a plastic one. We will not really care about specularity and roughness for now, but we'll then change the reflectance by changing the base colors. This is color based, so you don't plug in just a value for reflection. You actually need to plug in a color. So if you're used to like creating a color from, you know, 0 to 1, or creating a defining reflection using 0 to 1, you can do color HSV, and then in value, if I right click this, yeah, this should work from, yeah, you can see they're basically value defining the brightness. So I can just plug in 1.0 here. And if I plug that to 0.2, now it will be kind of a gray color. Right. Another option is to create a color or create a swatch, right? And if I go in here I also have the value, right? So I can just here set that to 20, and that should really be the same color as this color. Okay. This says that it's a gradient type. You can see the little icon there is a gradient type. Which is a bit complicated. We can talk about it now. So you can create gradients using Cyclops. You can either kind of use this, which is very similar to kind of the native gradient component, but this then outputs a gradient object. Okay. Or you can create a gradient like manually from parameters, change the interpolation, color space, and so on. This is used to display data on the hemisphere mesh, but it can also be used as an input onto a material. And I don't know how applicable it actually is in the analysis in this case, but basically what you can do is you can, like, I could do this, I could do a swatch. Okay, so I could do white and black. Okay, so then I say 0 and 1. Okay, and then we merge these. Sorry, so black and white. That's the parameters. No, sorry, that's the colors. And the parameters are 0 and 1. Okay. Okay, so now we have created a gradient instead of a solid color. So if I now input the gradient as a base color, this is a gradient-based material now, meaning that you can use the thing we call a parameter on the geometry to choose where in this gradient should I put the color. That basically means that the color sampling happens on the GPU instead of happening when you create the material. It is basically so that you don't need to create, like, let's say that you have you kind of create you have materials that span a lot of different colors in the gradient. You don't need to necessarily create a specific material for each color. You can create a color or a material that has a gradient as the base color and then sample the gradient. I cannot currently come up with an exact use case within this workflow, so I will just delete this. Okay, and I will keep this as the reflectance, and we get back on track. So we call this, maybe we can just call this material context. Materials. Okay. So now we plug that name here. So again, names are very important. The material is a separate object, which also needs to be added to the scene or to the analysis if you're not using a scene. And the way you apply a material onto a geometry is that you specify the material name that you want the geometry to use. Right, so here I've named the material. I also need to plug in the same name for the geometry, right? So now my New York context is using the material called context material. I can hover the geometry output here. You can see that in the description it says geometry, vertices, faces, and then it says the MAT, which is the material name. But we also then need to add the material to the scene. Okay, so I'm just gonna... Actually, we can just create all the materials kind of in a group. That might be the easiest way to do this. Okay, so we have our context material. We know it has these settings. Then we maybe have our floor material. Let's say that has reflectance of 0.4. We might have a ceiling. Let's call it ceiling wall as material, and we can set that to 0.6. Okay. So now we have 3 different materials. And I'll just copy this one down. And then we have another material, which will be the glazing. So I create another material. Now it needs to be a glass material and not the plastic material. Right, and on this we define a transmittance instead of reflection or base color like we do on the plastic. Okay, so let's call this class. Plug that into name. Transmittance, again, you can use this to create a transmittance if you want. If you don't want to use a swatch. So we can say now it's 0.2 transmittance. Maybe that's a bit conservative. Let's put that to 0.7. Okay, here you can change refractive index as well if that would be relevant, but in this case it's just glass, so we don't need to do that. So now we have all our materials, and we just merge this, and we group this. Okay, and then this is basically, we can call this static scene objects. Okay. And there we input the materials, we input the context, right? Because these things will be in the scene always. Yeah, let's add that here, and let's flatten that output. Okay, so we added our materials and we added our context, and we've defined that the context should use the context material. Okay, now we can, just gonna, let's turn off the display for a bit. Okay. Now we can start converting our geometry that we have up here. So let's create geometry for each of these. We have these, let's say that this is the windows or glazing. Okay, that's the glazing. And then here we have the wall. Sorry, the W on my keyboard is a bit slow. Glazing, wall, and maybe we can do this in here. That's this geometry. Wall. You see that I don't necessarily have to turn these into meshes, right? They will be meshed when they come in here. So in the case of these kind of simple things, I usually just plug them straight in. And this is exterior. Okay. And the glazing is using what material name? It is using the glass material. Okay. And then the wall and ceiling is using ceiling and wall material. So we have wall, and then I see that we haven't actually created anything for ceiling and floor yet, which are here. So first we had the floor, and then we had the ceiling. So let's see, the ceiling and the wall, they might as well go into the same because they have the same. They have the same material. Okay. And then the floor can go into a separate one. Obviously, you could just do all of this in the same data tree if you wanted to. Anyway, this one had a separate floor material, I remember. Maybe it was called floor material actually. And then we'll use the context material on the outside of the building. So exterior can use context material, floor can use floor material. Okay, and then we can merge all of these. So these are all our geometries, and we can just put them all in the same geometry group. Right. You can also see that when we plug in a mesh here, it's automatically triangulated because Cyclops does inevitably use triangulated meshes. Okay, we need to name this and make sure we're not using the same name as anything else. So here we have a context, and then we can name this. Let's just name it option. Okay, and as before, the context is not going to change very often. The material properties are maybe not going to change very often. So I just plug these into add objects, and then for this one will be dynamic, right? Because we might change the option or change the floor there as we were doing. Can delete this. Okay, this then also needs the analysis points, which are here. Okay, so that's now created the 1700 shading masks for the floor plate. Now that was very fast because we're using direct sampling here, meaning that none of these shading masks should actually have any shading or any relationship to the sky because there is geometry in the way pretty much all the way around. Okay, so then we can instead create another type of sampling setting. So you can do this custom, and this is quite good if you want to. So these settings, they are similar to the ones you will use in Radiance. And if you are comparing, like if you're comparing the results of Climate Studio with Cyclops or of Radiance, I saw there was a question about that from Craig, who seems to be going for everyone for presentations, or if you're comparing to Lady or Honeybee and Radiance, it's very important that these settings are the same, because just like if you've used Radiance, like if you just change the depth, from 3 to 6, it will completely change the results that you get out of Honeybee, that you get out of Climate Studio, and it's obviously the same here, right? So you need to really make sure that the depth and the sampling is similar or exactly the same if you want to be comparing apples to apples. Anyway, for this use case here, we'll just create sampling settings, and we'll use the preset analysis settings. And this is kind of a short way to just get specific analysis quality. Right, so you can see if you set this to low, you can see here in the, actually there's such a long description here, I'll plug it in here. You see, if I set it to analysis quality low, then the samples will be 2,500. We will be bouncing 4 times, and the threshold for the Russian roulette termination is 0 or 4E06. You can read more about the sampling settings in the documentation if you want to. Anyway, I'll plug this in. You can see now it's at least 27. If we set this to high, now it's suddenly 518 milliseconds because we're now tracing a lot more rays. I'll just keep it at medium and then we can change it later and see the impact. Okay, I mean, we can obviously measure the radiation, right, on the floor plate if we want to with bounces. Let's see. I assume that the values will be very, yeah. I mean, they're quite small. I guess the direct radiation is what's mostly relevant in this case. But let's see. So because we're using shading masks, that means that you can use, like, because we already have this description of the relationship between the analysis point and the sky, we can reuse that description, as we call it, or shading mask, for a lot of other analyses within the same workflow. And really the heavy lifting is the shading mask, right? That's where we're doing all the ray tracing to understand the impact of a specific patch onto the analysis point. So if I plug in, or if I drop down any daylight analysis here, if we look at daylight factor, you can see it takes a shading mask input. If we look at UDI, takes a shading mask, and they all take, well, the UDI also takes a sky series, obviously, because that is weather specific. The daylight factor is not weather specific. But all of these, I just plug in my shading mask, and in this case, my sky series. And now, obviously, it asks for an illuminance interval for the UDI. So I'll just plug in, I think it's usually 300 to 2000, if I remember correctly. Okay, that one was a bit slower. But yeah, so what's happening in these components is basically an enormous matrix multiplication of the sky data for each patch and the shading mask or the shading factor for each patch, right? So let's see if we can create some more visualizations here. Let's use the daylight factor, and we can use another preset for that. Okay, that doesn't really make sense. Sky type, generate missing enum, standard overcast sky. Just preview off on these. This. Maybe display. Let's just display the glazing and the wall here. So I'm just going to display the glazing and the wall in separate colors just to understand what is what. Let's change these display settings a bit. Okay. And then I think what's maybe a good daylight factor, 0.5. Let's just put an upper on 2% and the lower on 0. Okay, not very good daylight factor on this floor plate. At least not that I'm getting here. Let's see that everything is correct. Context material. Let's just see what happens if we change the glazing here. Okay, maybe the ceiling can be 0.8 just to liven this up. Let's give it a high bounce. Still not super. Hemisphere. This is a strange. Okay, I mean, maybe this is actually a fairly normal value. Just to make it a bit more colorful, I'll try and be a bit more optimistic in our materials. That doesn't seem to be affecting. Let's see. But the glazing is affecting. I guess my floor plate isn't great. Let's see what happens if I turn on this. Oh, okay, so there was probably dormant geometry within the scene. And that is a bit tricky, which you need to think of sometimes. Like, because we've been using the same script here to run the different analyses, and I had my analysis option from the other analysis, right? And I just deleted the geometry group with that specific name. Right? And then I created a new geometry group with another name, meaning that the old geometry group was actually dormant within the scene. So it's good to be wary of what you're like when you're using scenes, when you're not like running all the geometry straight into the analysis component. You really need to be wary of what you've added and what you removed. And if you run into something weird, you basically can, if I just select this and enable, this component reruns. And it will basically flush out anything and just kind of add the objects that you currently have plugged into the different components. Yeah, now our daylight factor looks a little bit more optimistic. And let's see if we can just display the context here as well. Yeah, you can obviously do the other ones here, like if I want to display UDI, maybe we can just copy these. To just see them. So this deconstruct domain, start and end. Okay, and this is the parameter. So there's UDI, meaning the amount of time within the time pattern or within the sky series that the illuminance is within this illuminance interval, right? So you can see this is a percentage. UDI low, the amount of time that it's below the interval. Obviously, this gets brighter in the center because it is more time in the center that's below the interval, and this gets bright only, I guess, in the kind of south, because we're in New York. No, we're actually in London with the New York context. That's confusing. Anyway, yeah, that is where it gets brighter. Okay, I hope that's kind of clear how you kind of set this up. I think so. Just if you're, again, just to reiterate, if you're comparing, it's good to make sure that your sampling settings are the same. And then obviously make sure that your material properties are also the same. Yeah, okay, maybe some display we can do just to show. So if I drop the hemisphere and I use the hemisphere mesh, which basically creates the mesh, and we can give that a scale. I don't know where we are in size here. Oh, obviously we need to input the hemisphere as well. Sorry. This is the hemisphere we're using. Okay, that's a bit pink. But then, for example, we can take the sky series, right? This contains a lot of data because it's basically data now for every point in time, every hour of the year for all the weather that we measured. So I can take the sky series, I can use the get property value, and then I can get the different skies. This would be one sky per hour, right? Because that's like one sky per sample in our time pattern. I can also get the cumulative sky, which would basically be the total amount, the cumulative data within a single cell. That gives me a sky with 145 cells. I can then use this again, get property value, right? Because this is another object. I can then get luminance from that sky. So you can have ground luminance, just like you specify here, ground reflectance, like you were doing. Radiance, you can also get the luminance cells, and they basically contain the data about each cell. Then from the luminance cell, you can get each individual value, right? So if I use get property value again, and I add this drop down, you can see I can get diffuse, luminance, radiance, and direct luminance, radiance, and the total luminance and radiance. So if we just use the diffuse there, and we get the bounds of these values, right? So this is the, you can see it's cumulative. Let's do diffuse radiance. So here you can see that basically the irradiance from each patch over the year, or sorry, the radiation from each patch over the year. So we get the bounds there, it's from 5,000 to 12,000. So now I can basically use those values as parameters, right? Because I have a hemisphere here with 145 cells, and here I have a sky based on the same hemisphere with 145 cells. So it's a value for each cell. I use that as my parameters. And then this will also need a gradient, right? Because it doesn't know yet which colors. So I create the gradient. Now this needs a Cyclops type gradient. And this component here, right, it creates an interactive gradient, but using a domain as an input. So I can use this domain here as the input to my gradient. I can use a preset maybe to green to red, and I plug that into gradient. And now we can see the cumulative data on the sky. Basically using the hemisphere, we can also see the direct cumulative data, right? So this would be for the sun as it moves over the sky. And we can, if maybe I just disable this for now. And, oh, I can just do that actually. That was, we can just plug in a higher value here just to see some prettier sky subdivision. Okay, so now we have 512 patches, or maybe just do like 1,000 patches. And now we're starting to see the impact of our sampling, right? Because this is the direct radiation or direct irradiance from each patch. And you can see because we sample just once per hour, it kind of becomes a bit spread out, or rather it's not spread out on the neighboring, like obviously the sun is also going to be here, right? It's just that it's moving this way and we're only checking once per hour. Meaning that it might be beneficial to use a time step which is a little bit, like use more time steps per hour instead of just one. Now, you can see already it takes a second to create the sky series because we now have 8,000 cells and we have we have 1,000 cells and we have 8,760 time steps. Right, so we're creating 8,700,000 values, basically. But why not create 6 steps per hour instead? So this is then going to take 6 seconds, hopefully. Yeah, there we go. And now suddenly we can see the direct is much more even, right? And our results should then be more accurate because we're doing a better sampling of the sky. You can look at the diffuse. Yeah. On the hemisphere, you can display data that's also related to the shading mask. So if I turn this on again, no, this might be a bit slow. Sorry. If I lock the solver, I'm going to disable this just for. Okay. So now we're creating a hemisphere, right? With 1,000 patches for each shading mask. So if I take a list item here, and just to visualize also which analysis point, like which shading mask we're looking at, we can do this. I'm gonna just take a point, set one point, set that here. Position. Okay, so we move that out of the way. Okay. So for the point that is here, right? That is the first point, the first shading mask in this list. I can get the shading factors, right? And this will be the multiplier for each patch in the sky. Okay. So you see now we have a list of numbers here, which are the multipliers for each patch. And that obviously then takes into account all the materials and the ray tracing we've done in order to evaluate that relationship. And then again, we can get the bounds. Are we getting the bounds here actually? Just do this then. Number, so that's the number. And then we plug in the shading factors here instead. Now this can be a bit confusing, but anyway, now we're looking at the shading mask for that specific point. Okay, so, and I guess like these very red patches, they would then be where the windows are in relation to that point, right? And if I just plug in 1,000 here, and let's see if we can just pick other ones just to exemplify. So as we step through here, you can see actually what parts of the sky are affecting this part of the development. And this data can actually be quite useful in different kind of very bespoke analysis. It can be good to kind of know this relationship. Okay, I don't know, maybe Wojciech and Ollie can come in here and see if you have any questions or any comments on what I'm going through.
I think this is pretty clear, Oscar. I'm trying to think if there's something we haven't covered, but
I think you guys have covered a lot of stuff. There's loads for people to go back and rewatch and jump into. There are some more technical questions, which are quite interesting. I think when you're using the gradient, someone's asking, does gradient likely to be used to simulate a gradient glass frit? Would that be, could you use it for that?
I guess you could, yes, but you would have to create a lot of geometry. But in theory, you could, because you could, like, you could have a. Let's see if I can do this. So if I take, how do I do this? Okay, I'm just gonna model this manually because that's just gonna be easy. Okay, so if I imagine this is my window. Okay, that's my window. So then in theory, you could create a subdivision like this, right? And then we could, I know I can do this in Grasshopper, but now I'm just doing it. Oh no, there was one as well. Oh no, that's the center. Yeah, sorry. Okay, let's just say that this is my geometry, okay? So if I then reference this geometry, right, then I would probably do a evaluate box, maybe, and I would deconstruct the point that's in the center of the box. I would sort these by the Z of the box, right? So then I have them, the lowest one is obviously the first one in the list, right? And then I create the geometry here, like a Cyclops geometry. I plug in my reference surfaces meshes. Let's just say I have created a material called gradient. Okay, so that's the name of the material, and then let's do a series count. Sorry.
list length.
Yeah, okay. Count. We can keep those values, it doesn't matter. Oh, okay, no, I'm just gonna remap to. Okay, so now I have numbers. I think there's a simpler way to actually do this. Now I have numbers 0 to 1, right? So then that can be my parameters. So now each mesh has a parameter of 0 to 1. So if now I create the material, which is glass then. No, we named it gradient material. So. Name, and then I create the gradient. And in theory, I could actually do this just manually, or just with the interactive one. I set this to white and black, and now we want, yeah. Let's say that with the ones that have the parameter 0 would get a black color. The ones that have the parameter 1 would get a white color, meaning being fully transparent. The domain is already set to 0 to 1. This goes into transmittance because transmittance is the gradient input. That should be it.
Yeah. Nice.
I hope that's clear. I'm not going to test it now, but this should, in theory anyway, produce a kind of, a gradient, of less transparent to more transparent glazing.
Yeah. No, I think that's great. You've covered a lot. I mean, there's little bits and bobs, but I think people are saying thank you. They're gonna come back over the videos and slowly go through it. We'll see what we can do with scripts and stuff, but there are templates on the website, right? People can download as well.
I mean, there are these, right? The tutorial files here.
Yeah.
And there's tutorial for every type of analysis here.
Yeah.
So and there's just maybe
Oscar. The file.
Yeah, and they're set up in a way where you can kind of just directly plug your own inputs, so it should be fairly easy. You just replace the context geometry with your own context, and it should work out of the box.
Yeah.
Some of them require you to input things like, obviously, if you run something weather dependent, you're gonna have to supply your own EPW or stuff like that.
Yeah. Okay, fantastic, guys. I think you've been going for. We're almost at the 4-hour mark, which is a long time to to present stuff. So I know it's exhausting. So guys, thank you. Everyone in the crowd, please give a thank you or any last minute questions. But really appreciate the time, guys. It's amazing what you built, and it's amazing that you've made this public to everyone. A lot of people in the comments are saying that I wish I had this a few years ago instead of waiting around for CPU analysis. But yeah, it's really great.
I mean, there's obviously always a lot of questions about Ladybug and if you should switch or which one you should use and stuff. And it's, we're not here to try and replace Ladybug or anything. We love the guys and we love the software. This is just a way to make the ray tracing part faster.
Yeah.
Use it for that. It's not like you need to replace your whole work for this. So much you can do in Honeybee and Ladybug that you will never be able to do in Cyclops. We're not trying to create something that replaces it. We're just trying to utilize the fast hardware, which is the GPU that you already have in your machine, to speed up the analysis that you're running.
Yeah, but you can really see for those computational workflows where you're trying different things, it's really going to be powerful.
Yeah, I mean, for optioneering, it just completely changes the game because you can start imagining things that you couldn't even imagine before. Like
Yeah. Also the scale of the models at which you can run it and the optimization is just unreal. But yeah, try it for yourself, guys, and happy to be here. So thank you, Oli.
Yeah.
Actually, one more thing which people have been asking for a long time. What do I buy hardware-wise to make my Rhino faster or to run my analysis faster, right? And with this tool, it is literally 99% depending on your GPU. If you get a better GPU, like I don't work for NVIDIA, but if you get a better GPU, your analysis is going to be better. And every year they just release new GPUs that are twice as fast next year, and twice as fast next year. Obviously, they cost you a kidney, but also the lower grade ones perform really well. And you can run this on old hardware; it performs really well. You look at the system requirements, but
and
it scales with the hardware that you have in your machine.
Yeah, and you need it for so many other things as well, like rendering, all that kind of stuff. So AI. So yeah, invest in a good GPU. All right, guys, feel free, Oscar, to unshare. We'll just do a little goodbye. I guess if anyone's got any questions for you guys or just wants to get in touch, I guess LinkedIn's the best place to reach you guys, would you say?
Yeah, probably. If you have anything Cyclops related, just post on the McNeil forum and tag Cyclops.
Okay.
And we try and answer them.
That way we can get the notification and kind of help out.
Yeah, and it helps others as well, right? If others have the same question.
Cool. And obviously this is all part of our build up to our event. We'll have you guys at our event. We'll have probably most of your team coming in and out at the event. Martha will be speaking as well. So if you guys want to kind of meet, part of the reason we called it a summit is because we have all this stuff going online. We're obviously an online platform. It's nice to just get in a room with with people physically and meet them. And so if anyone's out there, you want to come meet these guys and many other people, come and get a ticket and be part of it. there'll be lots of beers as well afterwards in the networking, which is where the magic happens. So come and check that out. Guys, thank you once again. For those of you who signed up on the website, we'll chop this up and put it onto the website as well. But for now, it'll live on here on YouTube. Oscar, Wojciech, thank you guys so much. And we'll hopefully see many of you at the summit.
Thank you.
All right. Cheers, guys.
Cheers.